The night sky holds many secrets, but on the 8th of November 2025, something extraordinary happened. An object from beyond our solar system, travelling through the darkness between the stars for billions of years, revealed itself in a way that has captured the attention of astronomers worldwide. This is the story of 3I Atlas, an interstellar visitor that is rewriting what we thought we knew about objects from other star systems. Chapter 1. The Radio Whisper from Beyond. In the early morning hours of October 24th, 2025, deep in the heart of South Africa, a remarkable discovery was made. The Meerkat radio telescope, with its 13.5-metre diameter dish, was pointing toward a specific region of the sky. What it detected would become the first radio signal ever captured from an interstellar object. The object in question was 3I Atlas, a comet-sized visitor from beyond our solar system, discovered just months earlier on July 1st. Unlike the countless comets born within our own solar neighbourhood, this one carries with it the chemical fingerprints of another star system, another time, another place in the galaxy. On that October morning, 3I Atlas was positioned at an angular separation of just 3.76 degrees from the Sun. To put that in perspective, that is only 7 times the diameter of the Sun as we see it in our sky. The object was threading through one of the most challenging observational windows possible, nearly lost in the overwhelming glare of our parent star. Yet Meerkat, operated by the South African Radio Astronomy Observatory, managed to pierce through the difficulties and detect something profound. Not a signal in the traditional sense, not some deliberate transmission beaming across the cosmos, but rather the chemical whisper of molecules being torn apart by starlight. The detection came in the form of radio absorption lines at very specific frequencies, 1.665 GHz and 1.667 GHz. These frequencies are the signature of hydroxyl radicals, molecules consisting of one oxygen atom bonded to one hydrogen atom, denoted chemically as OH. Hydroxyl is not just any molecule. It is what remains when water, that most precious substance for life as we know it, is broken apart by the intense radiation of the Sun. As water molecules evaporate from the surface or interior of 3I Atlas and drift into space, the ultraviolet light from the Sun strikes them with enough energy to shatter their bonds. The result is hydroxyl, along with free hydrogen atoms, drifting in the cold vacuum around the comet. The Meerkat team detected these hydroxyl molecules through a phenomenon known as Doppler shift. The absorption lines appeared at velocity shifts of negative 15.59 km per second and negative 15.65 km per second, with remarkably small uncertainties of just 0.16 and 0.17 km per second respectively. This Doppler shift tells us about motion. As 3I Atlas hurtled through space at nearly 100 km per second relative to Earth, the radio waves from the hydroxyl molecules were compressed or stretched, depending on the geometry of observation. The negative values indicate the object was moving in such a way that the radio waves appeared slightly blue-shifted, compressed to higher frequencies. The width of these absorption lines, measured as full width at half maximum, came in at 0.88 km per second for the first line and 1.26 km per second for the second. These widths are not random. They encode information about the temperature of the gas surrounding 3I Atlas. At the time of observation, the interstellar object was positioned 1.38 times farther from the Sun than Earth orbits. At this distance, with solar heating falling off, as the square of distance and cooling radiation rising as the fourth power of temperature, scientists calculated that the surface temperature of 3I Atlas would be approximately 230 degrees Kelvin. This is cold by human standards, roughly negative 43 degrees Celsius, but it is warm enough for certain ices to begin sublimating, transitioning directly from solid to gas. The thermal motion of hydroxyl molecules at this temperature produces a broadening effect on the spectral lines, and the observed widths matched the theoretical predictions almost perfectly. The agreement between theory and observation, at around 0.8 km per second, provided strong confirmation that what Meerkat detected was genuine hydroxyl emission from a real physical process. This was not the first time astronomers had tried to detect radio signals from 3I Atlas. Previous attempts on September 20th and September 28th had come up empty, but on October 24th, as the object emerged from behind the Sun, In what astronomers call solar conjunction, the signal finally appeared. The timing is significant. Solar conjunction occurred on October 21st, just 3 days before the successful detection. During conjunction, 3I Atlas was aligned almost perfectly between Earth and the Sun, making observation impossible due to the Sun's overwhelming brightness. But as it emerged from this alignment, travelling nearly perpendicular to our line of sight, Meerkat was ready. The detection of hydroxyl from 3I Atlas represents the first time we have captured a radio signal, however natural, from an interstellar visitor. It provides direct evidence that this object is releasing water vapour, and by extension, that it carries water ice within its structure. This is profound because water is not just important for life, it is a key ingredient in the chemistry of planetary systems. When we detect water or its breakdown products from an object born around another star, we are reading a message written in chemistry. We are learning that the basic building blocks we find here, in our own solar system, are not unique to our cosmic neighbourhood. They exist out there, among the stars, being carried from system to system by wandering objects like 3I Atlas. Harvard scientist Avi Loeb, who has been at the forefront of studying this interstellar visitor, described the detection in striking terms. He noted that the Doppler shift of the hydroxyl absorption results from the full speed of 3 Atlas relative to Earth, some 98 kilometers per second, multiplied by the sine of the angle between the direction of relative motion and Meerkat's line of sight. That angle, he calculated, was 9.2 degrees. This geometric relationship, this dance of velocities and angles, allowed astronomers to verify that what they were seeing was real. The radio waves were being absorbed by hydroxyl molecules in the coma surrounding 3I Atlas, molecules that were shed from its surface as sunlight warmed the ices beneath. The thermal speed of these molecules, derived from the surface temperature, yielded a broadening that matched observations. Coincidentally, Loeb had taught this exact phenomenon, thermal broadening of spectral lines, in his class on radiative processes in astrophysics at the Harvard Astronomy Department, just 1 month before the detection. Theory had predicted the observation, and observation had confirmed the theory. But this detection carries additional weight beyond the pure science. 5 weeks before the Meerkat observation, Avi Loeb had encouraged radio observatories to search for radio emissions from 3I Atlas. His motivation was not random. He had calculated something remarkable about the trajectory of this interstellar visitor. The arrival direction of 3I Atlas, when traced backward through space and time, coincides to within 9 degrees with the arrival direction of one of the most famous and mysterious signals ever detected, the WOW signal of 1977. On August 15th, 1977, Ohio State University's Big Ear Radio Telescope detected a strong narrowband radio signal at a frequency of 1.42 GHz. The signal was so unusual, so far beyond the normal background noise, that astronomer Jerry Eman circled it on the computer printout and wrote "WOW" in the margin. The name stuck. For 48 years, the WOW signal has remained unexplained. It lasted 72 seconds, the exact length of time the Big Ear telescope's beam would have remained pointed at a specific spot in the sky as Earth rotated. It was never detected again, despite numerous follow-up searches. Its origin remains one of the great mysteries of astronomy. Now, with 3I Atlas passing through our solar system, Loeb calculated that on August 12, 1977, just 3 days before the WOW signal was detected, the interstellar object was at a distance of about 600 times the Earth-Sun separation, or 600 astronomical units. At that distance, light travel time was about 3 days. The coordinates of 3I Atlas on that date were right ascension, 19 hours 40 minutes, or 295 degrees, and declination negative 19 degrees. The WOW signal originated from right ascension 19 hours 25 minutes, or 291 degrees, and declination negative 27 degrees. The separation is approximately 4 degrees in right ascension and 8 degrees in declination. The chance of 2 random directions in the sky being aligned to that level is about 0.6%, less than 1 in 100. If the WOW signal did originate from 3I Atlas, what kind of transmitter would be required? The detected intensity of the WOW signal ranged from 54 to 212 Jansky, with a bandwidth of about 10 kHz. At the distance of 600 astronomical units, this corresponds to a source power of 0.5 to 2 gigawatts. That is the output of a typical nuclear reactor on Earth. Not impossibly large for an advanced civilization, not even particularly exotic by our own technological standards, but remarkable nonetheless because it would suggest 3I Atlas carried or carries active technology. Loeb hoped that this coincidence in arrival direction would motivate radio observers to monitor 3I Atlas carefully, and they did. The Meerkat detection, while showing only natural hydroxyl absorption, rather than an artificial narrowband transmission, demonstrates that radio telescopes can and are watching this object. So far, there has been no report of any artificial radio transmission from 3I Atlas. The hydroxyl absorption signal is entirely consistent with natural processes, with sunlight breaking apart water molecules in the coma of a comet. But the story is far from over. On March 16th, 2026, 3I Atlas is expected to pass within 53 million kilometres of Jupiter. At that time, NASA's Juno spacecraft, orbiting the giant planet, will use its dipole antenna to search for radio signals from the interstellar visitor at low frequencies ranging from 50 Hz to 40 MHz. This is a different part of the radio spectrum than Meerkat observed. These lower frequencies are the realm of natural radio bursts from planets like Jupiter, emissions from the solar wind, and potentially, if they exist, low-frequency transmissions from artificial sources. The detection by Meerkat has accomplished several things. First, it provides the first direct evidence of water activity in 3I Atlas through the proxy of hydroxyl molecules. Second, it demonstrates that radio telescopes can successfully observe interstellar objects even under challenging conditions, nearly lost in the sun's glare. Third, it sets the stage for future observations as the object continues its journey through our solar system. But perhaps most importantly, it reminds us that even natural processes can appear mysterious and profound when viewed from a cosmic perspective. The hydroxyl molecules detected by Meerkat were created when water from another star system, carried for billions of years through the cold darkness between stars, was warmed by our sun and broken apart by its ultraviolet light. These molecules, drifting in the coma of 3I Atlas, are messengers from the distant past, from the protoplanetary disk that formed around some other star billions of years ago. They tell us that the chemistry of life's building blocks is universal, that water exists not just here but throughout the galaxy. As November 8th dawned, and astronomers analysed the Meerkat data, another observation was about to shake the astronomical community. Just hours later, in the pre-dawn darkness, telescopes would capture an image of 3I Atlas that revealed something no one had seen before in an interstellar object. A complex network of not one, not two, but 7 distinct jets. Chapter 2. 7 jets blazing in the night. At 4 hours 10 minutes. Universal time on November 8th, 2025, 3 astronomers were watching the sky. M. Yeager, G. Riemann, and E. Prosperi had their instruments trained on a specific patch of darkness, a region where 3 Atlas was known to be located. The interstellar object was positioned just 29 degrees from the sun in the sky. This is extraordinarily challenging for observation. At that small angular separation, the sun's light dominates everything. The sky is bright, even before dawn. Scattered light fills the atmosphere. Most astronomical objects would be completely overwhelmed, but 3's Atlas was not most objects. Despite being only 7 to 10 degrees above the horizon, despite the proximity to the sun's glare, the telescopes captured something remarkable. The team took 24 exposures in green filter light, each lasting 35 seconds. They also captured 2 exposures in red filter and 2 in blue filter. These images were then stacked, combined together to increase the signal and reduce the noise, revealing details that would be invisible in any single frame. What emerged from this process was extraordinary. 3 Atlas displayed a large glowing halo extending outward to nearly 500,000 kilometres, 500,000 kilometres, or 5 arc minutes on the sky. To put that in perspective, the diameter of the halo was larger than the distance from Earth to the Moon. But it was not the size of the halo alone that captured attention. It was the structure within it. Emanating from the central nucleus of 3I Atlas were at least 7 distinct jets of material. 7 separate streams of gas and dust, each with its own direction, its own character, its own story to tell. Comets often display jets. When sunlight warms the surface of a comet, Ice sublimating from specific vents or active regions can create collimated streams of gas and dust. These jets can be seen in many solar system comets, particularly as they approach the Sun and activity increases. But 7 jets from a single object is unusual. More unusual still is that some of these jets were pointing toward the Sun. These are called anti-tails, and while they can occur in solar system comets due to viewing geometry and the way dust particles spread out in orbit, seeing them so clearly in an interstellar object is rare. The anti-tails appear to point sunward because of the viewing angle from Earth. Dust particles released from the comet spread out in its orbital plane. When Earth passes through or near this plane, we can see the dust that lies between us and the comet, creating the illusion of a tail pointing toward the Sun rather than away from it. But the images from November 8th showed more than just geometric illusions. The 7 jets had different brightnesses, different lengths, different angles of emission from the nucleus. This suggests that 3I Atlas has multiple active regions on its surface, areas where sunlight penetrates to subsurface ice and creates localized sources of outgassing. The complexity of this jet structure had not been seen before in 3I Atlas. Earlier observations had shown simpler features, perhaps a single prominent jet or a diffuse coma. But as the object passed perihelion, its closest approach to the Sun on October 29th, and began to emerge back into observable sky, the increased solar heating had awakened multiple vents simultaneously. This raises a fundamental question that sits at the heart of the mystery surrounding 3I Atlas. Are these jets simply volatile vents from a natural nucleus, regions where ice deposits lie close to the surface and sublimate when warmed? Or could they represent something more controlled, something more deliberate? In the context of natural comets, multiple jets indicate a heterogeneous surface composition. The nucleus is not uniform. Some regions are rich in volatile ices that vaporize easily. Other regions are covered with darker, less volatile material that acts as an insulating layer. As the comet rotates, different regions face the Sun, and different jets activate. The rotation period of 3I Atlas has been estimated at approximately 16.2 hours based on brightness variations. As it spins, the 7 jets would sweep through space like the arms of a cosmic sprinkler, each one active when its source region faces the Sun. But there is another interpretation, one that Avi Loeb and others have raised in the context of this object. If 3I Atlas were not entirely natural, if it contained technology, or was itself a technological artifact, then multiple jets could represent controlled thrusters used for navigation. This idea is speculative, to be sure. There is no direct evidence that 3I Atlas is anything other than a natural comet. Its spectrum shows carbon dioxide, water, and other molecules expected from a comet. It has a coma and tail. It brightens as it approaches the Sun. In almost every measurable way, it behaves like comets we have observed for centuries. Yet there are anomalies. The trajectory of 3I Atlas is aligned to within 5 degrees of the ecliptic plane, the plane in which the planets orbit. This is statistically unlikely for a random interstellar object, which would be expected to arrive from any direction with equal probability. The chance of such alignment is about 0.2%. The mass of 3I Atlas is also unusual. Based on the lack of detectable non-gravitational acceleration, despite the observed outgassing, Loeb and colleagues calculated that its mass must exceed 33 billion tons. This corresponds to a solid nucleus diameter larger than 5 kilometers. For comparison, the first interstellar object, 1I Oumuamua, was estimated at around 400 meters in length. The second, 2I Borisov, had a nucleus around half a kilometer in diameter. 3I Atlas is potentially 10 times larger than Borisov, and more than 10 times larger than Oumuamua. Given the limited reservoir of heavy elements in interstellar space, we would expect to detect many small objects before finding one as large as 3I Atlas. The statistics suggest we should have discovered on the order of 100,000 objects the size of Oumuamua before encountering something as massive as 3I Atlas. Yet we have detected only 3 interstellar objects total. This makes 3I Atlas anomalous on statistical grounds alone. Add to this the unusual trajectory, the detection of nickel without corresponding iron in spectroscopic observations by the Very Large Telescope, and the timing that brings it close to multiple planets, and the picture becomes more complex. The 7 jets visible in the November 8th images add another layer to this complexity. If these are natural jets from volatile vents, then we are seeing a comet in an active phase, with multiple source regions outgassing simultaneously. The structure is beautiful, the physics is well understood, and there is no mystery beyond the standard processes of cometary science. If, however, these jets represent something else, if they are controlled in some way, then we are seeing something unprecedented. The question becomes not what is producing these jets, but why and for what purpose. Loeb has suggested that if 3I Atlas were to maneuver, if it were to release mini-probes, or if it were to transmit radio signals at frequencies indicating artificial origin, then we would know it is technological. So far, none of these behaviours have been observed. The hydroxyl detection by Meerkat is consistent with natural processes. The jets, while numerous and complex, are consistent with natural outgassing. But the story is not over. 3I Atlas is still being observed. On November the 17th, 2025, the Virtual Telescope Project has scheduled a special live observation session to capture new images of the interstellar visitor. Ground-based telescopes around the world continue to track its motion, its brightness, its spectral signature. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer, will observe 3I Atlas in early November as the spacecraft travels toward its own destination in the outer solar system. JUICE was not designed to study comets, but the opportunity to point its instruments at an interstellar object is too valuable to pass up. On December 19th, 2025, 3 Atlas will reach its closest approach to Earth, coming within approximately 267 million kilometres, or 1.8 astronomical units. This is nearly twice the distance from Earth to the Sun. It will not be a close encounter by any dramatic standard, but it will offer the best observing geometry from Earth for detailed study. The Hubble Space Telescope and the James Webb Space Telescope are both expected to observe 3I Atlas in December. These instruments, orbiting above Earth's atmosphere, can capture ultraviolet and infrared wavelengths that are blocked or distorted by our air. They can measure the composition of the coma, the temperature distribution across the nucleus, the size and structure of dust grains in the tail. On March 16th, 2026, as mentioned earlier, 3I Atlas will pass within 53 million kilometres of Jupiter. The Juno spacecraft will attempt radio observations at that time, but Juno's cameras might also be turned toward the visitor, potentially capturing resolved images of the nucleus itself. Throughout all of this, the 7 jets remain a focal point of study. Are they stable, or do they change as the comet rotates and as its distance from the Sun increases? Do new jets appear while old ones fade? Is there a pattern to their activity, a periodicity that matches the rotation of the nucleus? These questions will be answered only with continued observation, with patience, with the accumulation of data over weeks and months. But already, the November 8th observation has changed how we view 3I Atlas. It is not a simple object. It is not a uniform ball of ice and rock gently outgassing as it warms. It is complex, structured, active in multiple locations simultaneously. The image captured by Jaeger, Raymond and Prosperi shows a halo extending 500,000 kilometres, glowing in the reflected sunlight and the fluorescence of excited molecules. Within that halo, 7 jets trace paths outward from the nucleus, some stretching sunward as anti-tails, others extending in different directions, painting a picture of an object in the full throes of activity. This is what an interstellar comet looks like when it visits our solar system. This is the face of a wanderer from the galaxy, an object born perhaps 4 to 7 billion years ago in the protoplanetary disk around another star, cast out into the darkness, and now illuminated once again by the light of our sun. The jets of 3I Atlas are writing a message in gas and dust, a message about the physics, of ices under solar heating, about the interior structure of objects from beyond our system, about the diversity of worlds that exist in the galaxy. Whether that message speaks only of natural processes or hints at something more remains to be seen. As the news of the 7 jets spread through the astronomical community on November 8th, reactions range from scientific excitement to speculation about what this complex structure might mean. Some researchers focused on the natural interpretation, discussing sublimation rates and volatile distribution. Others allowed themselves to wonder if the structure suggested something more directed. What is certain is that 3I Atlas has become the most intensely studied interstellar object in history. More telescopes, more spacecraft, more observers are tracking its every move than ever turned toward Oumuamua or Borisov. The data accumulating in these weeks and months will shape our understanding of interstellar objects for years to come. The 7 jets of 3I Atlas captured on that November morning, just hours after the first radio detection from the object, represent a convergence of observations that is painting a picture of unprecedented detail. We're watching an interstellar visitor in real time, seeing it respond to the warmth of our sun, seeing it release the ices it has carried for eons through the cold between the stars. And as we watch, as we measure, as we analyse every photon of light and every molecule of gas, we are confronted with a fundamental question that transcends the specific case of this single object. In a galaxy of hundreds of billions of stars, in a universe of trillions of galaxies, how common are objects like 3I Atlas? How often does material from one star system journey to another? And in that vast network of exchange, that cosmic recycling of matter across the galaxy, could some of those wandering objects carry more than just ice and rock? Could they carry information? Could they carry technology? Could they carry, intentionally or not, the signature of intelligence? These questions hang over the observations like the coma hangs over the nucleus of 3I Atlas. They are not answered by the detection of hydroxyl or the imaging of 7 jets. They are not resolved by spectroscopy or photometry or astrometry. They require a different kind of inquiry, one that combines scientific rigour with philosophical openness, one that neither dismisses possibilities out of hand nor accepts them without evidence. For now, 3I Atlas continues its journey. The jets glow in the sunlight, the hydroxyl molecules drift through space, the radio telescopes listen, the optical telescopes watch, and humanity, for this brief moment in cosmic time, has the privilege of witnessing an object from beyond our solar system, sharing space with us, sharing the light of our sun, and sharing its secrets, one observation at a time. The convergence of the radio detection and the 7 jets imaging on November 8th, 2025, marks a milestone in the study of 3 Atlas. It is a day when multiple lines of evidence came together, when different observational techniques revealed complementary aspects of the same mysterious visitor. And it is a day that will be remembered in the history of astronomy as the moment when an interstellar object began to reveal its true complexity. But this is only the beginning. As we will see in the chapters ahead, 3 Atlas carries with it connections to one of the greatest mysteries of the 20th century, implications for the distribution of mass in the galaxy, evidence for the universality of water, and lessons about how we observe and interpret the cosmos. The story of 3I Atlas is far from over. In many ways, it is just beginning. Chapter 3. The WOW signal connection. The summer of 1977 was a pivotal moment in the search for extraterrestrial intelligence. While astronomers around the world scanned the heavens for signs of cosmic company, one radio telescope in Ohio was about to detect something that would perplex scientists for nearly 5 decades. The Big Ear radio telescope, operated by Ohio State University, was not the largest or most sophisticated instrument of its time. But on August 15th, 1977, it was pointed at exactly the right patch of sky at exactly the right moment. For 72 seconds, the telescope recorded a signal unlike anything seen before or since. The signal appeared at 1420.456 MHz, a frequency known as the hydrogen line. This is not a random choice in the radio spectrum. Hydrogen is the most abundant element in the universe, and the transition between its 2 lowest energy states produces radiation at this specific frequency. Since the 1960s, scientists involved in the search for extraterrestrial intelligence have theorized that any civilization attempting to communicate across interstellar distances might choose this frequency as a universal calling card. What made the August 15th signal so remarkable was its intensity and its narrow-band nature. The signal's strength jumped to 30 times the background noise level. It was focused within a very narrow frequency range, much narrower than natural astrophysical sources typically produce. Natural radio sources like pulsars, quasars or stellar flares tend to emit across broad frequency ranges. This signal was different. It was concentrated, powerful, and brief. Astronomer Jerry Eman was reviewing the computer printout of the telescope data when he noticed the anomaly. The intensity readings, normally showing 1s and 2s representing background noise, suddenly spiked to the alphanumeric code 6EQUJ5. In the system used to record intensity, this sequence represented the sharp peak of the signal. Emmons circled it with a red pen and wrote in the margin a single word that would define this mystery for generations. Wow! The telescope's design meant that any celestial object would remain in its beam for exactly 72 seconds, as Earth's rotation carried the antenna across the sky. The WOW signal lasted precisely this duration, suggesting its source was indeed something in the heavens rather than terrestrial interference. Then it vanished. Despite immediate follow-up observations and decades of subsequent searches, the signal never repeated. The source direction was determined to be in the constellation Sagittarius, at coordinates of right ascension, 19 hours 25 minutes, and declination -27 degrees. This region of sky lies toward the galactic centre, a direction rich with stars and interstellar gas, but also a direction from which determining a specific source becomes extraordinarily difficult due to the sheer density of objects. Over the decades, numerous explanations have been proposed for the WOW signal. Some researchers suggested it came from a passing comet, with the narrow-band emission arising from the hyperfine transition of hydrogen in the comet's extended cloud of neutral hydrogen. Others proposed it was a natural but transient astronomical event, perhaps a flare from a distant magnetar whose beam happened to sweep across Earth for a brief moment before moving on. In 2024, a team from the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo conducted a new analysis, creating what they claimed was the most precise characterization of the signal to date. Their work, part of the Arecibo WOW project, examined whether natural explanations could account for all the signal's properties. But even with modern analytical techniques, the mystery remained. Then, in 2025, as 3 Atlas was discovered and its trajectory calculated, Avi Loeb made a calculation that connected 2 seemingly unrelated cosmic phenomena, separated by 48 years. By backtracking the orbital path of 3I Atlas through space and time, Loeb determined where the object was on August 12, 1977, 3 days before the WOW signal detection. The light travel time of 3 days is significant because if something on, or associated with 3I Atlas, emitted the signal on August 12th, it would have reached Earth on August 15th. The interstellar object's position in 1977 placed it in a region of sky separated from the WOW signal's origin by approximately 9 degrees. 9 degrees is the angular width of about 18 full moons placed side by side. In the vast expanse of the celestial sphere, which encompasses 41,000 square degrees, this represents a remarkably close alignment. The probability of 2 random directions being aligned within 9 degrees is approximately 0.6%. While not conclusively proving a connection, this is far from the level of coincidence that can be casually dismissed. It is the kind of statistical alignment that demands attention, that suggests the possibility of a relationship between the 2 phenomena. If we entertain the hypothesis that 3I Atlas was the source of the WOW signal, several questions immediately arise. First, what kind of transmitter would be required to produce a signal of that intensity at a distance of 600 astronomical units? The WOW signal's intensity, measured at 54 to 212 Jansky, combined with the distance and the signal's narrowband nature, implies a source power in the range of 0.5 gigawatt to 2 gigawatts. For context, this is comparable to a large nuclear power reactor on Earth. It is not an impossibly large power output. A civilization with technology even modestly more advanced than our own could readily generate such power. The frequency also carries significance. The signal was slightly blue-shifted from the exact hydrogen line frequency by about 10 kilometers per second. This blue shift suggests the source was moving toward us at that velocity component. Interestingly, 3I Atlas has a velocity component toward the Sun that is consistent with producing such a blue shift, though the magnitude is somewhat smaller than the observed shift. The discrepancy is not perfect, but neither is it wildly incompatible. The duration of 72 seconds poses interesting questions. If 3I Atlas were the source, why would it transmit for exactly that length of time? One possibility is that the transmission was continuous but beamed in a specific direction, and Earth happened to pass through that beam as both it and the source moved through space. The 72-second observation window would then reflect the time it took for Earth's motion to carry us out of the beam, rather than the duration of the transmission itself. Another possibility is that the transmission was pulsed or intermittent, and we happened to catch one pulse. If Thru's Atlas were equipped with some form of beacon or signalling device, it might emit periodic bursts rather than a constant signal. We would need to observe the object at the same frequency for an extended period to detect any periodicity. The fact that the signal never repeated despite extensive follow-up observations has been one of the strongest arguments against it being an extraterrestrial transmission. The reasoning goes that any civilization attempting to signal across the galaxy would transmit repeatedly, making detection more likely. A single brief transmission seems wasteful and unlikely to be noticed. However, this argument assumes that any transmission from 3I Atlas in 1977 was intended as a deliberate signal rather than, say, leakage from internal systems, a brief diagnostic pulse, or even a targeted communication directed at a different recipient that Earth happened to overhear. It also assumes that the object's transmitter, if it exists, is still operational or still transmitting in the same way nearly 50 years later. The directional alignment between 3I Atlas and the WOW signal adds weight to another anomaly already noted about the object, its trajectory through the solar system. The orbit of 3I Atlas is aligned to within 5 degrees of the ecliptic plane, the flat disk in which Earth and the other planets orbit the Sun. For a random interstellar object, we would expect the trajectory to approach from any direction, with roughly equal probability. The fact that 3I Atlas comes in nearly along the ecliptic is itself unusual. Combined with the WOW signal connection, some researchers have speculated whether the trajectory might not be entirely random. If 3I Atlas were a probe sent by another civilization, choosing a trajectory along the ecliptic would be logical for encountering or observing planets. The ecliptic is where the action is in any star system, where terrestrial worlds and gas giants orbit, where conditions might support life. This speculation, it must be emphasized, remains highly theoretical. There is no direct evidence that 3I Atlas is anything other than a natural comet. Its composition, as measured by spectroscopy, shows carbon dioxide, water, and other molecules consistent with icy bodies. Its activity, including the 7 jets, can be explained by natural sublimation of volatiles. Its lack of detectable maneuvers or accelerations beyond what gravity predicts suggests an object moving passively through space. Yet the anomalies accumulate. The WOW signal alignment is one, the ecliptic trajectory is another, the unusual mass, the detection of nickel without iron, the timing that brings it close to multiple planets. All these factors individually have natural explanations, but collectively paint a picture that some find difficult to reconcile with pure chance. Loeb has been careful to frame his investigations not as claims that 3I Atlas is alien technology, but as explorations of possibilities that should not be dismissed without investigation. Science, he argues, advances by following evidence wherever it leads, and by maintaining intellectual humility in the face of the unknown. To declare with certainty that 3I Atlas is a natural comet before all the data are in is premature. To declare with certainty that it is technology is equally premature. The appropriate stance is curiosity coupled with rigorous observation. The WOW signal connection has motivated radio observatories around the world to direct their attention to 3I Atlas. The Meerkat detection proves that radio observations of the object are feasible. While that detection revealed only natural hydroxyl absorption, future observations at different frequencies and with different sensitivities might reveal other signals. The Juno spacecraft's planned observations in March 2026 will specifically search for low-frequency radio emissions from 3I Atlas. These frequencies, from 50 Hz to 40 MHz, are below what ground-based telescopes can effectively monitor due to Earth's ionosphere. If there are any artificial low-frequency transmissions from the object, Juno might detect them. Beyond the specific case of 3I Atlas, the WOW signal connection raises broader questions about how we search for and recognize potential signals from extraterrestrial civilizations. The original WOW signal, had it been received from the direction of a nearby star with known planets, would likely have received far more attention and follow-up resources. But coming from a direction in Sagittarius with thousands of stars and no obvious single source, it has remained an unsolved mystery. If the signal did indeed originate from an interstellar object passing through our solar system, it suggests that our search strategies might need to adapt. Rather than only monitoring fixed points in the sky around promising star systems, we might need to monitor moving objects, interstellar visitors that pass through our neighbourhood. The number of detectable interstellar objects is expected to increase dramatically in the coming decades as survey telescopes become more sensitive and more comprehensive. The Vera C. Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights, detecting asteroids, comets, and potentially interstellar objects much fainter and more distant than current surveys can reach. If interstellar objects are more common than previously thought, and if some fraction of them carry information or technology, then the rate of opportunities for detection increases. Each visitor becomes not just a scientific curiosity, but a potential message-bearing artifact, a piece of flotsam from the broader galaxy, carrying with it clues about worlds and civilizations beyond our own. The WOW signal remains one of the great unsolved mysteries of radio astronomy. The arrival of 3 Atlas from a closely aligned direction 48 years later adds a new dimension to that mystery. Whether the two phenomena are related through more than mere coincidence will require additional data, additional observations, and perhaps a dose of luck. What is certain is that the story of the WOW signal has been reopened by the discovery of 3I Atlas. Researchers who had moved on to other projects are taking another look. Radio astronomers are pointing their dishes at the interstellar visitor, and the public imagination, always captivated by the possibility of contact with other intelligences, has been reignited. In the decades since 1977, humanity has become more sophisticated in our search for extraterrestrial intelligence and in our understanding of the cosmos. We have discovered thousands of exoplanets, worlds orbiting other stars, many in the habitable zones where liquid water could exist. We have detected complex organic molecules in interstellar space and in the atmospheres of distant worlds. We have come to understand that the building blocks of life are common throughout the universe. Against this backdrop of growing cosmic awareness, the WOW signal and its potential connection to 3I Atlas take on added significance. They remind us that the universe is not just a collection of lifeless rocks and gas, but potentially a place of intelligence, of communication, of connection across the vast gulfs between stars. Whether 3I Atlas will ultimately prove to be a messenger from another civilization, or simply a natural comet that happens to have an interesting trajectory, its study has already enriched our understanding of the galaxy and our place within it, and that perhaps is the most important signal of all. Chapter 4. An anomalously massive visitor. When astronomers first detected 3I Atlas on July 1st, 2025, they knew immediately that it was special. Its hyperbolic trajectory marked it as only the 3rd confirmed interstellar object ever discovered. But as observations accumulated over the following weeks and months, a more profound realization emerged. This visitor was not just rare because of its origin, but because of its sheer size. The question of how large 3I Atlas actually is has been one of the most important and challenging aspects of studying this object. Unlike rocky asteroids that reflect sunlight predictably based on their surface area, comets are surrounded by clouds of gas and dust called comas that can make them appear larger and brighter than their solid nuclei actually are. When the Hubble Space Telescope turned its gaze toward 3I Atlas on July 21, 2025, it captured the sharpest image of the object obtained to that point. From a distance of 277 million kilometres, Hubble revealed a teardrop-shaped cocoon of dust extending from the nucleus. The background stars appeared as streaks because Hubble was tracking the comet's motion through space. These observations allowed astronomers to place constraints on the nucleus size. The upper limit came in at approximately 5.6 kilometres in diameter, though it could be as small as 440 metres. This broad range reflects the difficulty in separating the light reflected from the solid nucleus from the light scattered by surrounding dust and ice particles. By late August, as 3I Atlas continued to brighten and more data accumulated, researchers began to use a different approach to estimate the object's mass. Rather than trying to measure the nucleus directly, they analysed how the comet responded to its own outgassing. When a comet releases gas and dust from its sun-facing side, conservation of momentum means the comet experiences a reaction force, like a rocket. This force, called non-gravitational acceleration, causes the comet's trajectory to deviate slightly from a purely gravitational path. For small, low-mass comets, this effect can be quite pronounced. For massive objects, the same outgassing produces minimal deviation. A team led by Avi Loeb analysed over 4,000 observations of 3I Atlas spanning several months, from May 15th through September 23, 2025. They used data compiled by the Minor Planet Center to track the object's position with extraordinary precision. The accumulated observations had an uncertainty of just 0.028 arcseconds. The analysis revealed something remarkable. Despite clear evidence of outgassing from the spectroscopic data and visible jets in the images, there was no detectable non-gravitational acceleration. The upper limit was calculated at 15 meters per day squared. This absence of deviation, combined with the known mass loss rate from the comet's activity, led to a striking conclusion. To resist being pushed by its own outgassing, 3I Atlas must be massive, very massive. The calculations indicated that its mass must exceed 33 billion tons, or roughly 33 trillion kilograms. For a solid body with typical cometary density, this corresponds to a nucleus diameter of at least 5 kilometers. To put this in perspective, consider the two previous interstellar visitors. The first, 1I, Oumuamua, discovered in 2017, was estimated to be approximately 400 meters long with a highly elongated shape. The second, 2I Borisov, discovered in 2019, had a nucleus diameter estimated at around half a kilometer. 3 Atlas, with a minimum diameter of 5 kilometers, is therefore at least 10 times larger than Borisov and more than 10 times larger than Oumuamua in terms of linear size. But mass scales with volume, which scales as the cube of diameter. This means 3I Atlas is potentially 1,000 to 10,000 times more massive than either of its predecessors. This massive size creates a profound statistical problem. In interstellar space, the distribution of objects by size follows a predictable pattern, based on how planetary systems form and evolve. Smaller objects are vastly more common than larger ones. This makes intuitive sense. It takes less material and less specific circumstances to eject a small rock from a star system than to eject a mountain-sized body. Current models of planetary system formation and the ejection of debris into interstellar space suggest a steep size distribution. For every large object like 3I Atlas, there should be tens of thousands or even hundreds of thousands of smaller objects like Oumuamua. Yet humanity has detected only 3 interstellar objects total. We found Oumuamua first, then Borisov, then 3I Atlas. The fact that we discovered a massive object like 3I Atlas so early in our catalogue of interstellar visitors suggests one of several possibilities. First, our understanding of the size distribution of interstellar objects might be incorrect. Perhaps large objects are more common than models predict. This would require revising our theories of how planetary systems shed material into the galaxy. Second, detection biases might play a role. Larger objects reflect more light and are easier to detect at great distances. Perhaps there are indeed hundreds of thousands of small interstellar objects passing through the inner solar system every year, but they are too faint for current surveys to spot. Under this interpretation, 3I Atlas stands out not because it is statistically unlikely, but because it is bright enough to be noticed. Third, and most provocatively, 3I Atlas might not be a random sample from the natural population of interstellar objects. If its trajectory were somehow influenced or directed, if it were not purely a passive wanderer but something with intentionality, then the size distribution statistics would not apply. A technological artifact need not follow the same size distribution as natural debris. Loeb has emphasized that the unusual mass of 3I Atlas, particularly when combined with other anomalies, suggests the natural explanation may not be the complete story. The limited reservoir of heavy elements available for forming large rocky bodies in stellar systems, combined with the difficulty of ejecting such massive objects, makes 3I Atlas an outlier. If the nucleus diameter is confirmed to be larger than 5 kilometers through higher resolution imaging, then the natural origin becomes even more difficult to explain. The upcoming observation by NASA's Mars Reconnaissance Orbiter, using its HiRISE camera, if those images are released to the scientific community, could provide the resolution needed to measure the nucleus size directly. The mass of 3I Atlas also has implications for how we interpret its other properties. The lack of detectable non-gravitational acceleration, despite visible outgassing, is consistent with a massive nucleus. But it also means that if the object were to maneuver using any kind of propulsion system, that maneuver would need to be quite substantial to be detectable above the noise level of the observations. In other words, small course corrections or minor trajectory adjustments would be lost in the uncertainty of the measurements. Only a significant change in velocity, on the order of several meters per second or more, would be unambiguously detectable as a deviation from the gravitational path. This creates an interesting observational challenge. If 3I Atlas is entirely natural, then we expect its trajectory to be purely gravitational from here forward. Any detected maneuver would be strong evidence of non-natural origin. But the absence of detected maneuvers does not prove the object is natural, because subtle maneuvers could occur below the detection threshold. The Juno spacecraft's planned close approach in March 2026 offers an opportunity to measure the object's mass more directly through gravitational effects. When a massive object passes near a spacecraft, the spacecraft's trajectory is slightly deflected by the object's gravity. By precisely tracking Juno's position, astronomers can measure this deflection and infer the mass of 3I Atlas, independent of other methods. The massive size of 3I Atlas also affects how we think about its internal structure. A 5-kilometre nucleus contains an enormous volume of material. If this is primarily water ice, as suggested by the hydroxyl detections, then the object holds more than 10 trillion tons of water. This is comparable to the water content of some of the smaller moons in our own solar system. Such a large reservoir of ice would take an extraordinarily long time to sublimate away, even under the intense heating of a close solar pass. This might explain why 3I Atlas survived its journey through whatever star system ejected it billions of years ago, and retained enough volatiles to still be active when it arrived in our solar system. Smaller interstellar objects might lose their volatiles more quickly, either through sublimation during close stellar passes or through cosmic ray processing during the long journey through interstellar space. A massive object like 3I Atlas has enough bulk that its interior remains well insulated, preserving ancient ices that date back to the formation of its parent star system. The size of 3I Atlas also relates to its visible activity. The 7 jets observed on November 8th represent outgassing from specific locations on the nucleus. With a 5-kilometre diameter, the surface area of the nucleus is approximately 78 square kilometres. This is roughly the size of Manhattan Island. The jets, then, represent localised vents across this surface, perhaps only a few hundred metres or even tens of metres in diameter each. The fact that we can see 7 distinct jets suggests that the surface of 3I Atlas is heterogeneous, with some regions covered in volatile ices and others mantled by darker, less active material. This heterogeneity is common in solar system comets and likely results from the object's formation history and subsequent evolution. Different regions of the protoplanetary disk where the object formed had different compositions. Over billions of years, cosmic ray bombardment and occasional heating events might have processed the surface layers differently in different locations. The age of 3I Atlas remains uncertain, but is likely measured in billions of years. Some estimates place it between 4.6 and 7.6 billion years old, potentially making it older than our own Sun. If true, this ancient wanderer formed in the early days of the galaxy, when the first generation of stars more massive than the Sun had already lived and died, seeding the interstellar medium with heavy elements. An object this old has witnessed cosmic history on a scale difficult for humans to comprehend. It formed when the universe was less than half its current age. It has travelled through dozens or hundreds of star systems during its long journey. It has been bathed in the radiation of countless nearby supernovae. It carries within its frozen heart a record of conditions in the galaxy, billions of years in the past. The massive size of 3I Atlas ensures that this record is well preserved. Smaller objects are more easily altered by their environment, their surfaces eroded by micrometeorite impacts and radiation. But a 5-kilometre mountain of ice and rock is robust. Its interior, protected by meters of overlying material, remains relatively pristine. This makes 3I Atlas not just a visitor, but a time capsule. When we analyse the isotopic ratios of elements in its outgassed molecules, we are sampling the composition of the interstellar medium as it was billions of years ago. When we measure the abundance of different volatiles, we learn about the temperature and pressure conditions in the protoplanetary disk of an alien star system. The James Webb Space Telescope observations from August 6, 2025, revealed that 3I Atlas is releasing carbon dioxide at a rate consistent with its observed brightness and activity level. The spectroscopic data showed mass fractions of approximately 87% carbon dioxide, 9% carbon monoxide, and 4% water. This composition differs from typical solar system comets, which tend to be richer in water ice. The carbon dioxide dominance suggests that 3I Atlas formed in a colder region of its parent protoplanetary disk, farther from its star than the region where most solar system comets originated. Carbon dioxide ice condenses at lower temperatures than water ice, so its abundance indicates formation conditions that were particularly frigid. With such a massive reservoir of material, 3I Atlas represents an invaluable opportunity to study the composition of another star system. Each molecule that sublimates from its surface and drifts into the coma carries information about its birth environment. Each measurement adds a piece to the puzzle of how other solar systems formed and evolved. The question remains whether current theories of planetary system formation can adequately explain the existence of an object this massive as an interstellar wanderer. The calculations suggest we should not have encountered 3I Atlas so early in our survey of interstellar objects. We should have found multitudes of smaller visitors first. The fact that we did not might be telling us something important about the galaxy, about how material moves between star systems, or about the specific history of 3I Atlas. It is a reminder that our models, however sophisticated, are built on incomplete data. The universe continues to surprise us, continues to present phenomena that challenge our assumptions. 3I Atlas, with its 33 billion tons of mass concentrated in a nucleus at least 5 kilometers across, stands as one of the most massive interstellar objects we are ever likely to observe up close. Its study offers insights not just into this specific visitor, but into the population of objects drifting between the stars throughout the galaxy. Chapter 5. Water from another star system. In the vast darkness between stars, temperatures hover just a few degrees above absolute zero. Molecules move sluggishly, if at all. Ice is not just frozen, but locked in a crystalline stillness that can persist for billions of years. Yet even in this extreme cold, material survives, carrying with it the chemical signature of distant worlds and ancient times. When 3I Atlas entered the inner solar system in the summer of 2025, sunlight began to warm its frozen surface for the first time in eons. As temperatures rose, ice that had remained stable throughout the object's journey began to change state, sublimating directly from solid to gas without passing through a liquid phase. Among the molecules released was water, the universal solvent, the foundation of life as we know it. Detecting water from 3I Atlas proved to be a technical challenge that required some of the most sophisticated astronomical instruments available. The problem is that water itself does not emit visible light. Unlike gases such as oxygen or nitrogen that can fluoresce when excited by solar ultraviolet radiation, water remains largely invisible to optical telescopes. The key to detecting water from 3I Atlas came through observing its breakdown product, hydroxyl. When water molecules drift away from the comet's nucleus and into the surrounding coma, they encounter intense ultraviolet radiation from the sun. This radiation has enough energy to break the chemical bonds holding the water molecule together. The result is one hydroxyl radical, BOH, and one free hydrogen atom. Hydroxyl does emit detectable radiation. In the ultraviolet part of the spectrum, around 308 nanometers, hydroxyl molecules produce a characteristic glow. This wavelength is completely absorbed by Earth's atmosphere, making ground-based detection impossible. But from space, above the obscuring blanket of air, this hydroxyl signature becomes visible. NASA's Neil Gehrels Swift Observatory, a satellite designed primarily to study gamma-ray bursts and transient astronomical events, has a 30-centimeter telescope that can observe in both ultraviolet and optical wavelengths. Despite its modest size, Swift's position in orbit gives it a significant advantage for detecting the faint ultraviolet glow of hydroxyl. A team of physicists from Auburn University in Alabama, led by postdoctoral researcher Zexi Xing and principal investigator Professor Dennis Bodwitz, proposed observations of 3I Atlas with Swift. Their goal was ambitious: to detect hydroxyl from an interstellar object for the first time, providing direct evidence of water activity beyond our solar system's native population. The first observation campaign took place on July 31st and August 1st, 2025, when Thrisky Atlas was approximately 2.9 astronomical units from the Sun. At this distance, nearly 3 times farther than Earth orbits, most solar system comets remain quiet. The ESA's solar heating is insufficient to drive significant sublimation from their surfaces. These initial observations yielded only a marginal detection, a hint of signal but not enough for confident confirmation. The team needed more data. They scheduled a follow-up campaign for August 18th through 20th, increasing the exposure time and refining their observing strategy. To maximize the signal, the astronomers employed a technique called stacking. Each individual exposure lasted 30 seconds, short enough that the comet's motion across the sky would not blur the image. These exposures were then aligned based on the comet's predicted position and combined. The final dataset represented 2.3 hours of ultraviolet observations and 42 minutes in visible light. The visible light images served a crucial purpose. They showed how the comet appeared in reflected sunlight, primarily from dust particles in the coma. The ultraviolet images revealed gas emission. By comparing the two, the team could separate the dust signature from the gas signature. What emerged from this analysis was clear. The ultraviolet profile was broader than the visible light profile. This difference confirmed that the ultraviolet signal came from gas emission, rather than scattered sunlight. The gas, predominantly hydroxyl, extended farther from the nucleus than the dust, creating an extended halo of emission that traced the region where water molecules were being destroyed by solar radiation. The detection represented a major breakthrough. For the first time, astronomers had direct evidence of water activity in an interstellar object. The signal was unambiguous. The hydroxyl emission at 308.5 nanometers matched theoretical predictions for water breakdown products. The intensity of the emission allowed the team to calculate the rate at which 3I Atlas was losing water. The number was impressive, approximately 40 kilograms per second. To visualize this rate, imagine a fire hose running at full blast. That is roughly the rate at which water vapor was streaming off the surface of 3I Atlas as Swift observed it. Over the course of a day, this amounts to nearly 3.5 million kilograms of water lost to space. What makes this particularly remarkable is the distance from the Sun. At 2.9 astronomical units, far beyond the region where water ice easily sublimates in solar system comets, 3I Atlas was releasing water at a prodigious rate. This suggests something unusual about how the water is being liberated. The leading explanation involves ice grains rather than surface sublimation. Near-infrared observations from Gemini South and NASA's Infrared Telescope facility detected what appear to be small chunks of ice floating in the coma. These icy fragments, perhaps released from the nucleus through thermal fracturing or previous outgassing events, act like miniature steam vents. As sunlight warms these floating ice particles, they sublimate directly into the vacuum, releasing water vapor far from the nucleus itself. This extended source of water production explains how 3I Atlas can maintain such high outgassing rates at large distances where the nucleus surface should be too cold for direct sublimation. The Auburn University team's paper, published in the Astrophysical Journal Letters on September 30th, 2025, emphasized the significance of this detection. Dennis Bodowitz articulated it clearly. When we detect water or its faint ultraviolet echo from an interstellar comet, we are reading a note from another planetary system. This detection tells us that the ingredients for life's chemistry are not unique to our own corner of the galaxy. This is a profound statement. Water is not just any molecule. It is the medium in which terrestrial biochemistry operates. Every cell in every living organism on Earth contains water. Our bodies are roughly 60% water by mass. Life as we know it is fundamentally aquatic at the molecular level, even for organisms that live on land. The universality of water has long been suspected based on theoretical models of star and planet formation. Hydrogen and oxygen are among the most abundant elements in the universe. The formation of water molecules should be inevitable wherever these elements come together under suitable conditions. But suspecting universality and confirming it are different things. Previous interstellar objects provided mixed evidence. Oumuamua showed no signs of water or any other outgassing. it remained completely inert throughout its passage, exhibiting no coma, no tail, no activity whatsoever. This dryness contributed to the mystery surrounding its nature and led to speculation that it might not be a comet at all, but something else entirely. 2I Borisov, the second interstellar visitor, did show activity and was clearly a comet. Spectroscopic observations revealed the presence of carbon monoxide and cyanogen, but the water detection was less certain. Borisov's composition suggested it formed in a carbon monoxide-rich environment, potentially farther from its parent star than most solar system comets. Now, 3I Atlas provides the clearest evidence yet. The hydroxyl detection by SWIFT, confirmed at high statistical confidence, demonstrates unambiguously that this interstellar visitor carries water and is actively releasing it as it warms in our sun's light. The implications extend beyond confirming the presence of water. The detection allows astronomers to place 3I Atlas on the same comparative scale used for studying solar system comets. For decades, planetary scientists have used water production rates as a primary metric for characterizing cometary activity. By measuring how much water a comet releases at various distances from the Sun, researchers can infer properties of the nucleus, estimate the abundance of different ices, and track how activity evolves. With the SWIFT detection, 3I Atlas becomes the first interstellar object that can be directly compared to solar system comets using this standard metric. We can now ask quantitative questions. How does its water production rate compare to solar system comets at similar distances? Does it follow the same relationships between distance, temperature, and activity? Or does it show deviations that hint at different formation conditions? The answers to these questions will inform our understanding of how comets form around other stars. If 3I Atlas behaves like solar system comets, it suggests that the processes of planetary system formation are universal, producing similar objects regardless of stellar environment. If it shows differences, those differences point to variations in formation conditions, perhaps related to the metallicity of its parent star, the architecture of that planetary system, or the specific history of how material was processed in that protoplanetary disk. The detection also validates the observing strategy for future interstellar objects. SWIFT is not a large telescope. Its 30-centimeter aperture is smaller than many amateur instruments. What makes it powerful is its position in space and its ability to observe ultraviolet wavelengths. This demonstrates that detecting water from interstellar visitors does not require the largest and most expensive facilities. It requires the right instruments at the right wavelengths. As survey telescopes become more capable and interstellar object discoveries become more frequent, this lesson will be important. Not every detection will have access to Hubble or Webb for detailed study, but smaller, nimbler space telescopes like SWIFT can play crucial roles in characterizing these visitors. The European Space Agency's ExoMars Trace Gas Orbiter also contributed to the water story. On October 3rd, 2025, as 3I Atlas passed within 29 million kilometers of Mars, TGO's CASS's camera captured images of the comet. Though designed for imaging Mars' surface, the instrument successfully detected 3I Atlas as a fuzzy white dot against the star field. These Mars orbiter observations, while not providing the same chemical information as SWIFT's ultraviolet spectroscopy, confirmed the comet's position and brightness, contributing to the overall characterization of the object during a critical phase of its solar system passage. The story of water detection from 3I Atlas is also a story of international collaboration. The Auburn University team that led the SWIFT analysis, the European teams operating Mars orbiters, the observers at Gemini and IRTF who detected ice grains, and theorists around the world working to interpret the data all contributed pieces to the puzzle. This collaborative approach is essential for studying transient events like interstellar object passages. Unlike permanent features of the sky that can be observed repeatedly over years or decades, 3I Atlas is a fleeting visitor. Each phase of its passage through the inner solar system offers limited opportunities. Coordinating observations across multiple facilities and multiple wavelengths maximizes the scientific return from these rare encounters. The water production rate of 40 kilograms per second, sustained over the weeks of observation, implies that 3I Atlas has lost hundreds of millions of kilograms of water during its current solar system passage. Yet given its estimated mass of 33 billion kilograms or more, this loss represents only a tiny fraction of its total inventory. The vast bulk of the object's water remains locked in ice beneath the surface, insulated from solar heating. This reservoir of ancient water, formed billions of years ago in the disk around another star, has travelled across light years of space to temporarily visit our solar system. Each water molecule now being broken apart by our sun's ultraviolet light carries a history written in its isotopic composition. The ratio of deuterium to hydrogen, the relative abundance of oxygen 16 to oxygen 18, these isotopic signatures encode information about temperature and conditions during formation. While Swift's observations could not measure isotopic ratios directly, future spectroscopic observations with higher resolution instruments might achieve this. The James Webb Space Telescope, with its infrared spectrographs, could potentially detect absorption lines from water and other molecules in the coma with sufficient detail to determine isotopic compositions. Such measurements would answer fundamental questions about 3I Atlas's origin. Do its isotopic ratios resemble those of solar system comets, suggesting similar formation conditions? Or do they differ, pointing to a different stellar environment with different deuterium enrichment or oxygen processing? The detection of water from 3I Atlas stands as one of the defining discoveries of this interstellar visitor's passage. It confirms that water, the molecule we associate most closely with life, exists not just in our solar system, but as a common component of objects born around other stars. It demonstrates that interstellar space is not empty, but populated with wandering icebergs that carry water between star systems. And it raises a tantalizing question. If water is universal, if the building blocks of life are distributed throughout the galaxy on objects like 3I Atlas, then how often does life itself arise? The detection does not answer this question, but it shifts the probabilities, suggesting that the raw materials necessary for life as we know it are not rare but common, not localized but widespread across the galactic disk. Chapter 6. The Acid Test at Perihelion, October 29, 2025, 7:47 a.m. Eastern Time. At that precise moment, 3I Atlas reached perihelion, the point in its hyperbolic trajectory closest to the Sun. After billions of years wandering through the cold between stars after months of warming as it fell inward through our planetary system, the interstellar visitor arrived at the moment of maximum solar heating. The distance at perihelion was 1.356 astronomical units, approximately 203 million kilometers. For perspective, this placed 3I Atlas just inside the orbit of Mars but well outside Earth's path. The object would not approach dangerously close to any planet. But for a comet, perihelion represents the most critical phase of its journey. At this distance, the Sun's radiation delivers approximately 770 watts per square metre to the surface of 3I Atlas. This is about half the intensity that strikes Earth's surface at noon on a clear day. While that might not sound extreme, for a frozen body that has spent eons at temperatures near absolute zero, it represents an enormous influx of energy. Avi Loeb described perihelion as the acid test of 3R Atlas. The reasoning is straightforward. If the object is a natural comet held together primarily by weak intermolecular forces between ice crystals, the intense heating might break it apart. Comets can and do fragment, especially during close solar passes. The thermal stress, combined with outgassing pressure from rapidly sublimating ice, can overcome the weak gravity holding the nucleus together. A 5-kilometre object has surface gravity far too weak to hold itself together through gravitational attraction alone. Instead, comets rely on the intrinsic strength of their material, essentially being held together by the same forces that prevent an ice cube from spontaneously falling apart on Earth. But heat those forces sufficiently, allow internal pressure to build from vaporizing ice, and fragmentation becomes possible. If 3I Atlas were to break up at perihelion, the result would be spectacular. Multiple fragments, each with increased surface area exposed to sunlight, would sublimate far more rapidly than the intact nucleus. The result would be a dramatic brightening, a plume of gas and dust orders of magnitude larger than what preceded it. Such an outburst would be visible from Earth once the object emerged from behind the Sun. Conversely, if 3 Atlas were technologically manufactured, if its structure involved materials with high tensile strength or active systems maintaining integrity, then perihelion might present a different kind of test. For a spacecraft, the close solar pass represents an opportunity. The gravitational assist from the Sun can be used to modify trajectory, to accelerate or decelerate, to adjust course toward a specific target. Perihelion also represents the optimal moment for a mothership to release smaller probes. In the context of interstellar exploration strategies discussed by exobiology researchers, a large carrier vehicle might transport multiple smaller spacecraft, deploying them at strategic points to investigate different worlds in a target system. The Sun's proximity would provide maximum gravitational focusing for dispersing probes toward the outer planets. These scenarios remained theoretical. The critical observation was that humanity could not directly watch 3I Atlas during perihelion. The geometry placed the object behind the Sun from Earth's perspective. Solar conjunction, when 3I Atlas was aligned with the Sun, occurred on October 21st, 8 days before perihelion. At perihelion itself, the object remained lost in the Sun's glare. This unfavourable viewing geometry struck some observers as suspicious. Loeb had calculated that the trajectory of 3I Atlas, if deliberately planned, could hardly have been better designed to hide the object from terrestrial observation during the most critical moment of its solar system passage. The timing placed 3 Atlas behind the Sun precisely when it was closest, precisely when any unusual activity would be most likely to occur. Of course, this argument cuts both ways. If the trajectory were natural, then the conjunction timing would be pure coincidence. Thousands of comets have passed through the inner solar system over the centuries, and many have been poorly positioned for observation during perihelion. The fact that 3I Atlas shared this property could be simple bad luck from an observational standpoint. What saved the perihelion observations from being completely blind were space-based assets positioned away from the Earth-Sun line. Several spacecraft with different vantage points had the ability to observe 3I Atlas, even when Earth-based telescopes could not. NASA's Solar Terrestrial Relations Observatory, STEREO, consists of spacecraft that orbit the Sun at different rates than Earth. Stereo A orbits slightly faster, while the now-defunct Stereo B orbited slightly slower. These offset positions allow the spacecraft to observe solar phenomena from different angles, particularly useful for studying coronal mass ejections and space weather. In late October, Stereo A had a favourable viewing angle toward 3I Atlas. The spacecraft's coronagraphs, designed to block the bright disk of the Sun to observe the fainter corona, could also capture images of the comet passing through the inner solar system. Additionally, the GOES 19 satellite, a geostationary weather satellite operated by NOAA, carries a chronograph called CCOR-1. This instrument, primarily used for monitoring the Sun's outer atmosphere and detecting solar storms that might impact Earth's magnetosphere, also captured images of 3I Atlas during its perihelion passage. Citizen scientist Warshate Boonplod discovered the comet in CCOR-1 images, demonstrating that careful examination of publicly available data by dedicated amateurs continues to contribute to astronomical discoveries even in the age of professional all-sky surveys. The European Space Agency's solar orbiter, designed to study the Sun from closer vantage points than Earth, also had potential viewing opportunities. While its primary mission focuses on solar physics, the spacecraft's instruments could potentially observe bright comets passing through its field of view. A consortium of researchers, including teams from NASA and ESA, analysed the space-based imagery as it became available. What they found was both expected and surprising. The comet brightened rapidly as it approached perihelion, consistent with increasing sublimation rates as solar heating intensified. Peak brightness reached approximately magnitude 7 to 8, far brighter than it had appeared from Earth-based telescopes in the months prior. But the colour was unexpected. Processing of images from multiple wavelengths revealed that 3I Atlas appeared bluer than the Sun itself. This was profoundly unusual. Cometary dust typically reddens reflected sunlight, because the dust grains scatter blue light more effectively than red, removing blue from the direct beam. The surface of a comet, being much colder than the Sun, should also emit at longer, redder wavelengths. For 3I Atlas to appear blue meant either the dust properties were highly unusual, or there was a source of emission at blue wavelengths beyond just reflected sunlight. Some molecules in cometary comas, particularly carbon radicals like C2, emit strongly in the blue and violet part of the spectrum. A high abundance of these molecules could produce the observed colour, but another explanation, more speculative, suggested that if the object contained any heat source hotter than the Sun's surface temperature of 5,800 degrees Kelvin, such as an engine or reactor, the thermal emission from that source could shift the overall colour toward the blue. The rapid brightening far exceeded what models predicted for typical Oort cloud comets at similar distances. The authors of the observational paper stated explicitly that the reason for 3 Atlas's rapid brightening remains unclear. This is the language scientists use when the data exceed their theoretical framework, when the observations show something unexpected that current models cannot adequately explain. As October 29th passed and 3 Atlas began its outbound journey, the critical question was whether it remained intact. Did the object survive perihelion as a coherent body, or did it fragment into multiple pieces? If it survived, did its trajectory remain purely gravitational, or were there signs of manoeuvres, of course corrections, of non-gravitational accelerations? The answer would take time to emerge. The object remained behind the Sun for days after perihelion. Gradually, as Earth's orbital motion and the comet's outbound trajectory changed the viewing geometry, 3I Atlas would become observable again. The first ground-based telescopes to reacquire the object would likely be those in the southern hemisphere, given the comet's position relative to the ecliptic. ESA's Jupiter Icy Moons Explorer, JUICE, was scheduled to observe 3I Atlas in early November. Launched in April 2023, JUICE was on a route to the Jovian system, where it would study Europa, Ganymede and Callisto beginning in the early 2030s. But in November 2025, the spacecraft's trajectory placed it at a favourable position to observe the interstellar visitor. JUICE carries a suite of instruments including optical cameras, infrared and ultraviolet spectrographs, and a magnetometer. While the comet observation was not part of the mission's primary science goals, the opportunity was too valuable to ignore. The spacecraft's instruments could characterize 3I Atlas with a different viewing geometry than Earth-based observatories, potentially revealing features invisible from our planet. On November 3rd, 3Z Atlas passed within 97 million kilometres of Venus. This close approach, while not close enough for the Venusian gravitational field to significantly perturb the trajectory, placed the comet within range of potential observation by spacecraft orbiting the second planet. The Japanese Akatsuki Orbiter and ESA's Venus Express, though the latter's mission ended in 2014, demonstrated that planetary orbiters can contribute to comet studies when opportunities arise. No Venus observations of 3I Atlas were reported, but the close approach illustrated how the comet's trajectory threaded through the inner solar system, passing near multiple planets in sequence. The timing raised questions that Loeb and others had emphasized. Mars in early October, perihelion behind the Sun in late October, Venus in early November, then Earth approach in December, followed by Jupiter in March. This succession of near passes to major bodies in the solar system is not impossible for a random interstellar trajectory, but it is statistically uncommon. The probability calculations depend on assumptions about the initial distribution of interstellar object trajectories. If we assume objects arrive from random directions with random velocities, then the chance of one passing close to multiple planets is low. But if we account for gravitational focusing by the Sun, which tends to bend trajectories toward the ecliptic plane, the probability increases. Still, 3I Atlas's trajectory, with only 5 degrees inclination to the ecliptic, represents an extreme case of such alignment. Combined with the timing that brings it close to planets at regular intervals, the trajectory invites scrutiny. At perihelion, the Sun's gravitational field delivered the maximum velocity boost available. For a spacecraft, this ob-Earth maneuver, accelerating when deep in a gravity well, is the most efficient way to change speed. Any technological civilization with interstellar ambitions would understand and exploit this principle. The fact that no obvious maneuvers were detected does not prove they did not occur. Small trajectory corrections, adjustments of a few meters per second, would be lost in the uncertainty of position measurements. Only gross changes, accelerations of tens of meters per second or more, would be unambiguously detected. As 3I Atlas emerged from perihelion, astronomers worldwide prepared their instruments for the post-passage observations. The object's brightness, its spectral signature, its trajectory, all would be measured with renewed intensity. any deviations from predictions would be noted and analysed. The coming weeks would reveal whether the interstellar visitor had survived its closest solar approach intact or had fragmented into multiple pieces, whether it continued on a purely gravitational path or showed signs of course changes, whether its activity increased, decreased, or remained constant as it moved back into the cold outer solar system. Perihelion, the acid test, had passed. The object had been subjected to the most intense heating it would experience in our system. It had passed behind the Sun at the critical moment, hidden from terrestrial view but potentially observed by space-based assets with favourable geometry. Now, as it re-emerged into the morning sky, the next chapter of observations would begin. The results from perihelion would shape the scientific narrative around 3i Atlas for months and years to come. If the object showed signs of unusual behaviour, if it had manoeuvred or fragmented in unexpected ways, the implications would be profound. If it continued to behave as a natural comet throughout the passage, it would still represent an invaluable opportunity to study an ancient visitor from the galaxy. Either way, perihelion marked the midpoint of 3i Atlas's journey through our solar system. It arrived from the deep darkness between stars, passed through our planetary neighbourhood, and would soon depart back into that darkness, carrying with it whatever secrets it holds. The observations at perihelion, when finally compiled and analysed, would form a critical part of understanding this enigmatic visitor. Chapter 7. Chemistry of an Alien World. Every comet carries within its frozen heart a chemical archive of the conditions under which it formed. The relative abundances of different molecules, the isotopic ratios of elements, the presence or absence of specific compounds, all encode information about temperature, pressure, radiation environment, and stellar composition billions of years in the past. For 3i Atlas, this archive comes from another star system entirely, offering a window into planetary formation beyond our Sun. The first detailed chemical analysis of 3i Atlas came from the James Webb Space Telescope on August 6, 2025. Webb's near-infrared spectrograph instrument observed the comet for several hours, capturing the spectrum of light from the coma. This spectrum, showing how much light is absorbed or emitted at each wavelength, acts as a chemical fingerprint revealing which molecules are present. The results showed a comet dominated by carbon dioxide. Approximately 87% of the outgassing by mass was CO2, with 9% carbon monoxide and just 4% water. This composition is strikingly different from most solar system comets, which tend to be water-rich with CO2 as a secondary component. The carbon dioxide dominance tells a story about where, in its parent protoplanetary disk, 3i Atlas formed. Carbon dioxide ice condenses from gas at temperatures around 60 to 80 degrees Kelvin at typical nebula pressures. Water ice condenses at higher temperatures, around 150 degrees Kelvin. This temperature difference means that in a protoplanetary disk, water ice forms closer to the star where it is warmer, while carbon dioxide ice forms farther out where temperatures are lower. The composition of 3i Atlas suggests formation in the outer reaches of its parent system, analogous to the regions in our solar system where Uranus, Neptune and the Kuiper Belt objects reside. In our system, comets from the Oort cloud, which formed between the giant planets and were subsequently scattered outward, tend to have compositions reflecting that mid-distance origin. But comets from the scattered disk beyond Neptune show different compositions influenced by the colder formation temperatures. The 9% carbon monoxide is also significant. CO is even more volatile than carbon dioxide, condensing at temperatures around 20 to 30 degrees Kelvin. Its presence indicates that 3i Atlas formed cold enough to trap carbon monoxide ice, or that CO formed through chemical processing of other carbon-bearing molecules in the ice matrix. The low water abundance, just 4%, initially surprised observers given the strong hydroxyl detection by the Swift telescope. However, these measurements are not contradictory. The Swift observations measured the rate of water production, which was high in absolute terms even if water constituted a small fraction of the total volatile inventory. With a massive nucleus constantly replenishing the coma with fresh material, even a minor component by mass can produce substantial absolute quantities. The spectroscopic observations also revealed the presence of other molecules in smaller amounts. Methane, ammonia, and various organic compounds were detected at levels of fractions of a percent to a few percent. These molecules, while minor components, are scientifically valuable. because they provide additional constraints on formation conditions and chemical processing history. One of the most intriguing aspects of the chemical analysis came from observations by the Very Large Telescope in Chile. Using high-resolution spectroscopy, the VLT team detected emission lines from nickel in the coma of 3I Atlas. This by itself is not unprecedented. Gaseous metals including iron, nickel, sodium and magnesium have been detected in comets before, thought to originate from dust grains heated by sunlight. What made the VLT observation noteworthy was the apparent absence of corresponding iron lines. Typically, nickel and iron appear together in similar ratios because they are chemically similar, have similar cosmic abundances, and form together in stellar nucleosynthesis. The detection of nickel without iron suggests either an unusual abundance ratio in the material or a detection effect where iron lines happen to fall in regions of the spectrum that were difficult to observe. Loeb noted that industrially manufactured nickel alloys, particularly those used in high temperature or corrosive environments, sometimes have nickel content without significant iron. Certain stainless steels and superalloys can be nickel-rich. This observation, combined with other anomalies, added fuel to speculation about whether 3I Atlas might contain manufactured materials. However, most astronomers interpreted the nickel detection as evidence of standard cometary composition, with observational biases affecting the iron detection. Natural nickel-bearing minerals exist in meteorites and asteroids, and there is no requirement that processed cometary dust maintain cosmic abundance ratios. The colour of 3I Atlas changed noticeably over the course of its passage through the inner solar system. Early observations in July and August showed a reddish hue typical of comets with dusty comas. The red colour arises from complex organic compounds called tholins, carbon-rich polymers that form through irradiation of simpler organic molecules over long time periods. Then, during a total lunar eclipse on September 7, 2025, astronomers Michael Jager and Gerald Riemann captured images showing that 3I Atlas had turned green. This dramatic colour change, from red to emerald green, indicated a shift in the dominant emission mechanism. Green comets are not unusual. The green colour typically comes from diatomic carbon, C2, and the cyanogen radical, Cn. These molecules fluoresce strongly when excited by solar ultraviolet radiation, emitting green light at wavelengths around 510 to 520 nanometers. The appearance of strong green emission suggested that 3I Atlas had entered a phase of enhanced chemical activity, with solar radiation breaking down larger carbon-bearing molecules into these reactive radicals. The colour change could reflect either the rotation of the nucleus exposing regions with different composition, or an overall increase in cometary activity as the object approached perihelion. The green glow persisted for several weeks before the comet disappeared into solar conjunction in October. After perihelion, space-based coronagraphs observed that 3I Atlas appeared unusually blue. This blue colour, unexpected for dust-reflecting sunlight, might indicate a different dominant emission mechanism. Strong emission from molecules or ions in the blue part of the spectrum or thermal emission from a hot source could produce this appearance. The Spherex Infrared Space Observatory also contributed to the chemical characterization. Observations in September 2025 provided additional constraints on the infrared emission from the coma, helping to distinguish between scattered sunlight and thermal emission from dust grains of various sizes and temperatures. The data from Spherex, combined with Webb and ground-based infrared telescopes, allowed astronomers to model the size distribution of dust particles in the coma. This distribution affects how the comet scatters light and how much force solar radiation pressure exerts on the particles. Understanding dust properties is crucial for interpreting the overall activity and evolution of the comet. One unexpected feature in the early observations was the appearance of an anti-tail. Most comets display tails pointing away from the sun, swept back by solar wind and radiation pressure. But in July and August, 3I Atlas showed a distinct feature extending toward the sun. Anti-tails can occur through purely geometric effects. When Earth passes through or near the orbital plane of a comet, we see dust particles that were released earlier and now lie between us and the comet. These particles, still moving in their own orbits, can appear as a tail pointing sunward. However, the anti-tail of 3I Atlas was noted as particularly prominent and persistent. Some researchers suggested that the anti-tail might not be entirely a geometric illusion, but could include contributions from active jets pointing sunward. The 7 jets observed in November included some oriented toward the Sun, supporting this interpretation. Such jets would require active venting from regions on the day side of the nucleus, the hemisphere facing the Sun. The chemical evolution of the coma over time provided insights into how different ices respond to solar heating. Carbon dioxide, being more volatile than water, began outgassing at larger distances from the Sun. As 3 Atlas approached perihelion, water activity increased, though it remained a minor component compared to CO2. This evolution is consistent with a layered structure in the nucleus, with more volatile ices accessible near the surface and less volatile ices buried deeper. The Gemini South telescope captured particularly detailed images in late August, using multi-filter photometry. By observing at several different wavelengths simultaneously, astronomers could isolate the contributions from different gas species and dust. The technique, while not providing the spectral resolution of spectrographs, offers spatial information about where in the coma different emissions originate. These observations showed that the gas distribution extended much farther from the nucleus than the dust distribution. Gas molecules, being lighter, are less affected by solar radiation pressure and can travel farther before being ionized or photodissociated. The asymmetry in the distribution provided clues about the wind patterns in the coma and how solar radiation structures the outflowing material. Temperature measurements of the nucleus surface proved challenging but were estimated from thermal models based on the observed brightness and distance from the Sun. At perihelion, surface temperatures likely reached around 250 to 300 degrees Kelvin in sunlit regions. This is well above the sublimation temperature of carbon dioxide ice at the near-vacuum conditions of space, explaining the intense activity observed. On the night side of the nucleus, temperatures would be far lower, possibly dropping to below 100 degrees Kelvin. This large temperature gradient between day and night would drive thermal stresses in the nucleus material, potentially contributing to fracturing and creating the pathways for internal ice to reach the surface and sublimate. The rotation period of 16.2 hours, inferred from brightness variations, means that any given spot on the surface experiences roughly 8 hours of sunlight, followed by 8 hours of darkness. During the sunlit period, volatile ices sublimate vigorously. During the dark period, exposed surfaces cool and may develop fresh frost layers as gases recondense. This diurnal cycle of heating and cooling, sublimation and recondensation sculpts the surface morphology of comets. Over the course of a perihelion passage, this cycle can significantly alter the appearance and activity of the nucleus, stripping away layers of material and exposing fresh ice beneath. The chemical data from 3I Atlas will continue to be analysed for years to come. Each spectral line, each molecular abundance, each isotopic ratio provides a piece of the puzzle. Comparisons with solar system comets reveal both similarities and differences, gradually building a picture of how planetary systems throughout the galaxy produce and process icy bodies. The dominance of carbon dioxide in 3I Atlas is unusual but not unique. Some solar system comets, particularly those from the outer edges of the Oort cloud, show enhanced CO2 abundances, but the ratio in 3I Atlas is more extreme than any native solar system comet observed to date. This suggests that its parent star system had different conditions, perhaps a different inventory of available volatiles or different temperatures in the outer disk regions. The presence of organic molecules, including the tholins responsible for the red colour and the cyanogen creating the green glow, indicates that complex carbon chemistry operates in other stellar systems just as it does here. These molecules, formed through radiation processing of simpler compounds, are thought to be precursors to even more complex organic chemistry that could eventually lead to life. In this sense, every interstellar comet is a sample return mission, delivering material from another star system directly to our astronomical instruments. The chemistry we measure is not from some abstract distant world, but from material we can directly observe and characterize. It is as close as we can currently come to visiting another planetary system in person. The chemical archive stored in 3I Atlas spans billions of years. The ice is condensed in the protoplanetary disk of its parent star when that star was young. They were incorporated into planetesimals, the building blocks of planets, during the chaotic early phases of system formation. At some point, gravitational interactions with giant planets ejected the object into interstellar space. For billions of years, the chemistry remained frozen, preserved in the cold darkness. Cosmic rays slowly processed the surface layers, breaking chemical bonds and creating new compounds. But the interior remained largely unaltered, a pristine sample of ancient stellar system chemistry. Now, as sunlight from our sun warms this ancient ice and releases its molecules into space, we have the opportunity to analyse chemistry from billions of years ago and hundreds of light years away. Each measurement adds to our understanding of how stars and planets form, how chemical diversity arises across the galaxy, and how the building blocks of life are distributed through the cosmos. Chapter 8. Trajectory through time. Understanding the path of 3i Atlas requires thinking across vastly different scales of space and time. The object's current trajectory through our solar system, precisely mapped over months of observation, represents just the most recent chapter in a journey that has spanned billions of years and crossed a significant fraction of the galactic disk. The orbit of 3i Atlas is hyperbolic, meaning it is not gravitationally bound to the Sun. Its orbital eccentricity is approximately 6.1, far greater than the value of 1 that separates closed elliptical orbits from open hyperbolic trajectories. This high eccentricity, combined with its velocity and direction, proves beyond doubt that the object originated outside our solar system. When astronomers trace the trajectory backward in time, following the path through space that 3i Atlas took to arrive at our Sun, they find that it came from the direction of Sagittarius, toward the galactic centre. The object has been travelling through interstellar space for an estimated 4.6 to 7.6 billion years, based on its velocity and probable point of origin. This age range is remarkable. The lower bound, 4.6 billion years, coincides with the age of our own solar system. If 3i Atlas is indeed that old, it formed at roughly the same epoch as Earth and the other planets, but around a different star, perhaps hundreds of light years from where our Sun was born. The upper bound, 7.6 billion years, would make it older than the Sun itself, a relic from an earlier generation of stellar system formation. The velocity of 3i Atlas relative to the Sun is approximately 58 kilometers per second. This might seem fast compared to speeds we experience in daily life, but in the context of stellar motions in the galaxy, it is actually quite modest. Stars in the solar neighbourhood orbit the galactic centre at speeds around 220 kilometers per second. The relative velocity between nearby stars is typically tens of kilometers per second. What this modest velocity suggests is that 3i Atlas originated relatively nearby in galactic terms. It did not come screaming in from some distant spiral arm at hundreds of kilometers per second. Instead, it has been moving through the same general region of the galaxy as our Sun, both objects participating in the grand rotation of the galactic disk. The trajectory is oriented at an inclination of approximately 5 degrees relative to the ecliptic plane. This near alignment with the plane of the planets is one of the statistical anomalies that has drawn attention. Random interstellar objects should arrive from any direction with equal probability. The fact that 3i Atlas approaches nearly along the ecliptic is unexpected. One natural explanation involves gravitational focusing. As an interstellar object approaches a star, the star's gravity bends its trajectory, with the degree of bending depending on the object's velocity and closest approach distance. This focusing effect tends to concentrate trajectories toward the ecliptic plane because objects approaching from high inclinations are bent less than those already close to the plane. However, detailed modelling suggests that gravitational focusing alone cannot fully account for the very low 5-degree inclination of 3i Atlas. The probability of such alignment for a random trajectory remains around 0.2%, even after accounting for focusing effects. The retrograde nature of the orbit adds another layer of interest. 3i Atlas is moving through the inner solar system in the opposite direction to the planet's orbital motion. It approached from ahead in the direction of the solar system's motion through the galaxy, passed through the planetary system, and is now departing behind us. This retrograde trajectory has important implications for encounter velocities. When 3i Atlas passed Mars on October 3rd, the relative velocity was lower than it would have been for a prograde orbit, because the planet's orbital motion partially cancelled the comet's velocity. Conversely, when it passes Earth in December, the relative velocity will be higher because Earth is moving away from the approaching comet. The series of planetary encounters is a notable feature of the trajectory. Mars approach in early October at 29 million kilometres, perihelion on October 29th at 203 million kilometres from the Sun, Venus approach on November 3rd at 97 million kilometres, Earth's closest approach on December 19th at 269 million kilometres, Jupiter encounter on March 16th, 2026 at 53 million kilometres. This sequence, particularly the closer approaches to Mars and Jupiter, provides rare opportunities for spacecraft observations. The Mars Reconnaissance Orbiter, with its high-resolution imaging science experiment camera, had the potential to capture resolved images of 3I Atlas's nucleus from a distance of just a few tens of millions of kilometres. Such images could directly measure the nucleus size and possibly reveal surface features. As of early November, there have been calls for NASA to release any high-rise images of 3I Atlas to the scientific community. Congresswoman Anna Paulina Luna has advocated for this release, recognising the scientific value and public interest in understanding this interstellar visitor. Whether such images exist and what they might show remains to be seen. The Juno spacecraft's encounter with 3I Atlas in March 2026 presents another valuable opportunity. Juno orbits Jupiter in a highly elliptical orbit that takes it from close flybys of the giant planet out to distances of several million kilometres. If the timing aligns favourably, Juno could observe 3 Atlas from a distance of tens of millions of kilometres. Juno carries instruments designed to study Jupiter's magnetosphere, auroras and internal structure. However, some of these instruments can be repurposed for observing other targets. The spacecraft's dipole antenna, used to measure radio emissions from Jupiter, could search for radio signals from 3I Atlas at low frequencies inaccessible from Earth. The trajectory after leaving our solar system will carry 3I Atlas back into interstellar space, where it will continue wandering the galaxy for another few billion years. Its velocity relative to the Sun, slightly increased by the gravitational interaction with our star, will remain around 60 to 70 kilometers per second. At this speed, it will take roughly 10,000 years to travel 1 light year. In about 50,000 years, 3I Atlas will have travelled roughly 5 light years from our Sun, potentially passing through the outer reaches of another star system. In 1,000,000 years, it could encounter dozens of stars. Over billions of years, it might pass through thousands of stellar systems, a cosmic wanderer carrying with it material and perhaps information from world to world. This perspective transforms how we think about interstellar objects. They are not isolated curiosities, but participants in a galaxy-wide exchange of material. Every star system sheds material into interstellar space through various mechanisms: gravitational scattering by giant planets, stellar winds during the star's evolution, and eventual dispersal when the star dies. Simultaneously, every star system receives material from interstellar space. The Sun, over its 4.6 billion year lifetime, has likely captured or been visited by thousands of interstellar objects. Most were too small or too fast to be detected with pre-21st century technology, but they pass through nonetheless, briefly warmed by our Sun before continuing their journeys. The discovery rate of interstellar objects is expected to increase dramatically in the coming decade. The Virasi-Rubin Observatory, when operational, will scan the entire visible sky every few nights with sufficient sensitivity to detect objects far fainter than current surveys. Estimates suggest the Rubin Observatory could detect several interstellar objects per year, building a statistical sample that will reveal the population characteristics. Each new discovery will allow astronomers to refine models of the size distribution, velocity distribution, and composition distribution of interstellar objects. These distributions encode information about how common planetary systems eject material, how material evolves during long journeys through interstellar space, and how the galaxy's chemical composition has changed over time. The trajectory of 3I Atlas also provides clues about galactic dynamics. The modest relative velocity and the direction of approach suggest the object originated in the local stellar neighbourhood. By analysing the trajectories of multiple interstellar objects, astronomers can map the flow of material through our region of the galaxy. This flow is not random, it is shaped by the spiral arms, by the density waves that propagate through the galactic disk, by the cluster of stars that form together with the Sun and have since dispersed. Each interstellar object carries velocity information that, when combined with many others, paints a picture of how matter cycles through the galaxy. The backward integration of 3I Atlas's trajectory is limited by uncertainties in its velocity and position measurements. While we can trace the path back for thousands or even millions of years with reasonable confidence, going back billions of years to identify its specific star of origin is currently impossible. The accumulated errors grow with time, and the motion of stars themselves means that the stellar configuration billions of years ago was completely different from today. However, statistical approaches can constrain the general region of origin. The velocity and direction suggest a formation distance from the galactic centre similar to the Sun's current position, about 26,000 light-years. The age estimates suggest formation when the galaxy was younger and the interstellar medium had different composition, with fewer heavy elements than today. The fact that 3I Atlas survived billions of years of wandering says something about its structural integrity. Collisions with dust grains, cosmic ray bombardment, gravitational perturbations from passing stars all gradually wear away at interstellar objects. Small objects break apart or are eroded away. Large, robust objects like 3I Atlas can survive for galactic timescales. This survival bias means that the interstellar objects we detect tend to be older and larger than the typical debris ejected from planetary systems. The population we observe is not representative of what gets ejected, but rather of what survives the journey. The trajectory through our solar system, from inbound leg through perihelion to outbound leg, spans about 2 years from first detection to final observation. This brief window represents our only opportunity to study this visitor before it departs back into the darkness between stars. Every observation, every measurement, every data point collected during this passage contributes to our understanding not just of this object, but of the galaxy as a whole. As 3 Atlas moves outbound past Earth in November and approaches Jupiter in March, telescopes around the world will continue tracking its motion. Each night's observation improves the orbital solution, reduces the uncertainties, and enables better predictions of where the object will be in the future. The trajectory tells a story of cosmic wandering, of an object born billions of years ago around another star, ejected into the void, travelling across light-years of space, and now passing briefly through our solar system before continuing its eternal journey. It is a trajectory that connects stars across space and time, that demonstrates the dynamic nature of the galaxy, that reminds us that the space between stars is not empty but filled with wandering worlds carrying messages from the past. Chapter 9. The Scientific Community Responds. The discovery of 3I Atlas on July 1st, 2025, triggered a cascade of activity across the global astronomical community. Within hours of the initial detection by the Atlas Survey Telescope in Chile, observatories around the world were alerting their networks, coordinating observations, and mobilizing resources to study this rare visitor. The rapid response protocol developed after the discoveries of Oumuamua and 2I Borisov proved invaluable. Those earlier interstellar objects had caught the community somewhat unprepared, with precious time lost as researchers scrambled to organize observations. By 2025, the procedures were established, the contact networks were active, and the astronomical community was ready. The Minor Planet Center at the Harvard-Smithsonian Center for Astrophysics served as the central clearinghouse for observations. As data poured in from telescopes worldwide, the MPC compiled positions, calculated preliminary orbits, and disseminated information through astronomical telegram circulars. Within days of discovery, over 100 observations had been logged, constraining the orbits sufficiently to confirm the hyperbolic trajectory. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, which made the discovery, deserves recognition for its role. Funded by NASA and operated by the University of Hawaii, ATLAS consists of 4 telescopes distributed around the globe, 2 in Hawaii, 1 in Chile, and 1 in South Africa. The system is designed to detect asteroids that might pose impact threats to Earth, scanning the entire accessible sky every couple of nights. The fact that ATLAS detected 3I Atlas speaks to the system's capability. At apparent magnitude 17.8 at discovery, the object was quite faint, far below naked eye visibility, requiring dedicated survey telescopes with wide fields of view to find against the background of millions of stars and galaxies. Archive searches through previously collected data revealed that multiple telescopes had actually imaged 3E Atlas before the official discovery date. The Zwicky Transient Facility at Palomar Observatory in California had captured the object as early as June 14th, but the transient detection algorithms had not flagged it as interesting. Only after the discovery were these earlier images recognized for what they contained. This is common in astronomy. The sky is so vast and contains so many variable objects that automated surveys cannot flag everything interesting in real time. Often, discoveries are made by one facility and confirmed by archive searches through data from others. The coordination between survey teams allows these pre-discovery detections to be found and incorporated into the orbit calculations. The Hubble Space Telescope observation on July 21st represented one of the highest profile early studies. Securing Hubble time requires submitting proposals months in advance for most programs, but the telescope maintains a director's discretionary time allocation for targets of opportunity like supernovae, gamma-ray burst afterglows, or interstellar objects. The Hubble observation required careful planning. Tracking a moving target demands that the telescope continuously adjust its pointing to keep the object centered, while it streams across the sky at significant angular velocity. For distant objects like 3I Atlas, this tracking causes background stars to trail in the image, creating the characteristic streak seen in the famous Hubble picture. Despite the challenges, Hubble's resolution and sensitivity provided the sharpest view of the nucleus obtained during the early months. The images reveal the teardrop-shaped coma and provided crucial constraints on nucleus size, even if they could not directly resolve the nucleus as a discrete object. The James Webb Space Telescope observation on August 6th represented an even more complex target of opportunity. Webb, the largest and most powerful space telescope ever built, observes primarily in infrared wavelengths. Its instruments can detect the thermal emission from cometary dust and the infrared signatures of various molecules. Observing a moving target with Webb requires precise coordination between the telescope's pointing system and the prediction of where the target will be. Any error in the predicted position means the target might fall outside the narrow field of view of Webb's instruments. The successful observation demonstrated the capability of the astronomical community to rapidly organize observations of unpredictable targets with the most advanced facilities. Ground-based observatories also played crucial roles. The European Southern Observatory's Very Large Telescope in Chile, consisting of 4 8.2-metre telescopes that can operate independently or be combined for interferometry, provided high-resolution spectroscopy. The VLT's instruments span ultraviolet through infrared wavelengths, offering comprehensive characterization of the comet's emission. The Gemini Observatory, with its twin 8-metre telescopes in Hawaii and Chile, captured images and spectra at multiple wavelengths. The Gemini multi-object spectrograph allowed simultaneous observation of the comet and calibration stars, ensuring accurate measurements of the brightness and colour. Smaller facilities contributed as well. Amateur astronomers with advanced equipment participated in the observation campaign, providing light curves that tracked the comet's brightness over time. These observations, while not having the resolution or wavelength coverage of professional facilities, offered valuable time series data showing how the comet's activity evolved day by day. The coordination extended beyond optical and infrared telescopes. Radio observatories, after Avi Loeb's article about the potential connection to the WOW signal, began monitoring 3I Atlas. Meerkat's successful detection of hydroxyl absorption in October demonstrated the value of multi-wavelength approaches to studying interstellar objects. Space missions en route to other destinations adjusted their plans, where possible, to observe the visitor. ESA's JUICE spacecraft, travelling toward Jupiter, reprogrammed its instruments for a brief observation window in November. The ExoMars Trace Gas Orbiter, despite being in Martian orbit far from the comet's trajectory, successfully captured images during 3I Atlas's October Mars flyby. This multi-mission coordination illustrated a broader trend in space exploration. As more spacecraft populate the inner solar system and journey to the outer planets, opportunities increase for bonus science targeting unexpected phenomena. The infrastructure built for studying planets can be leveraged to study interstellar visitors. The NASA Mars Reconnaissance Orbiter represented perhaps the most anticipated potential observation. With its high-resolution imaging science experiment camera, capable of resolving features less than a metre across on Mars's surface, HiRISE could theoretically image the nucleus of 3I Atlas with unprecedented detail from the relatively close distance of tens of millions of kilometres during the October Mars approach. Whether HiRISE successfully observed the comet and what those images might show remains a matter of public interest and some controversy. Congresswoman Anna Paulina Luna's involvement in requesting the release of any such images highlighted the intersection of scientific research, government funding, and public transparency. The debate around potential HiRISE images reflects broader questions about how rapidly data from publicly funded missions should be made available. Traditionally, science teams have exclusive access to their data for a proprietary period, typically 6 months to a year, allowing them time to analyse results and publish papers before the data becomes public. For targets of intense public interest like interstellar objects, pressure grows to accelerate this release. The argument is that the public, having funded the missions, has a right to see the results as quickly as possible. Counter-arguments note that precipitous data release without proper analysis can lead to misinterpretation and sensationalism. The scientific community's response to 3I Atlas also included extensive theoretical work. Within weeks of discovery, papers began appearing on preprint servers analysing various aspects of the object. Orbit calculations, composition models, statistical analyses of its properties relative to other interstellar objects all contributed to a rapidly growing body of knowledge. Avi Loeb became the most publicly visible scientist studying 3I Atlas, publishing frequent articles on Medium and participating in numerous media interviews. His willingness to discuss both natural and technological interpretations of the object's properties generated both support and criticism within the community. Some researchers appreciated the open-minded approach, arguing that science progresses by considering all possibilities consistent with available evidence. The anomalies exhibited by 3I Atlas, from trajectory to mass to chemical composition, deserve careful investigation rather than dismissal. Others felt that discussing technological possibilities prematurely risked sensationalizing the discovery and misleading the public about the evidence. The scientific consensus, represented by the majority of published research, treats 3I Atlas as a natural but unusual comet requiring further study. This tension between open speculation and conservative interpretation is not unique to interstellar objects. It appears whenever astronomy encounters phenomena that challenge existing frameworks, from pulsars initially dubbed LGM for little green men, to fast radio bursts that spawned exotic explanations before natural mechanisms were identified. The healthy scientific approach requires balancing open-mindedness with skepticism, following evidence rigorously while remaining aware of cognitive biases and the human tendency to see patterns and intentionality where none may exist. The community's response to 3I Atlas reflected this balance, with mainstream publications focusing on detailed observations and measurements, while allowing space for speculative discussion about implications. International collaboration proved essential throughout the observation campaign. Telescopes in the northern and southern hemispheres provided continuous coverage as Earth's rotation brought different longitudes into darkness. The global network ensured that critical phases of the object's passage, particularly the brightest periods around perihelion, were captured by multiple facilities. The Virtual Telescope Project, an online platform providing public access to remotely operated telescopes, scheduled special observation sessions allowing citizen scientists to view 3I Atlas in real time. These events, while not contributing new scientific data per se, served the important function of engaging public interest and demonstrating the excitement of astronomical discovery. Educational institutions incorporated 3I Atlas into curricula, using the visitor as a case study for teaching orbital mechanics, spectroscopy, and the scientific method. Students calculated orbits from position data, analysed spectra to identify molecules, and debated the interpretation of anomalous properties. The object became a pedagogical tool demonstrating how real science unfolds. Media coverage ranged from accurate scientific reporting to sensationalized speculation about alien probes. Major news outlets interviewed astronomers, published visualizations of the trajectory, and explained the significance of studying material from other star systems. Tabloid publications ran with more fantastic interpretations, headlines screaming about possible extraterrestrial technology. Navigating this media landscape required scientists to communicate carefully, explaining uncertainties honestly while not overstating confidence in any particular interpretation. The phrase, "we don't know yet," appeared frequently in interviews, reflecting the reality that studying a rapidly moving, never-before-seen object takes time and involves considerable uncertainty. Social media amplified both accurate information and misinformation. Amateur astronomy communities shared images and discussed observations. Conspiracy theorists proposed elaborate scenarios. Science communicators worked to separate evidence from speculation, explaining what was actually known versus what was conjectured. The response by professional societies included special sessions at conferences, webinars for members, and rapid publication tracks for papers about 3I Atlas. The American Astronomical Society, the European Astronomical Society, and other organizations recognized the significance of the discovery and facilitated information sharing among researchers. Funding agencies responded by issuing special calls for proposals related to interstellar objects. NASA, ESA, and national funding bodies in various countries recognized that the study of these visitors represents a new frontier in solar system science. Supporting this research through dedicated funding streams acknowledges its importance and ensures continued progress. The Breakthrough Listen initiative, funded by the Breakthrough Prize Foundation and dedicated to searching for evidence of technological civilizations, included 3I Atlas in its observation program. Using radio telescopes around the world, this project searched for narrowband signals that might indicate artificial transmitters. No such signals were detected, but the observations set limits on how powerful any transmitter would need to be to evade detection. The scientific community's response to 3I Atlas ultimately reflected astronomy at its best. Rapid mobilization of resources, international collaboration, rigorous data collection, open debate about interpretation, and honest communication of both what is known and what remains uncertain. The object challenged the community to think broadly while maintaining analytical rigor, to be open to surprising possibilities while demanding extraordinary evidence for extraordinary claims. As observations continue through the end of 2025 and into 2026, the collaborative nature of the study will remain essential. No single telescope, no single research group, can fully characterize an object this complex and fleeting. Only through pooling observations, sharing data, and combining expertise across many institutions can the full story of 3I Atlas be told. Chapter 10. What 3I Atlas teaches us. As 3I Atlas moves outbound from our Sun, heading back into the darkness between stars, the astronomical community begins the process of synthesizing everything learned from this remarkable visitor. The story of this object extends far beyond the specific measurements and observations. It reveals deeper truths about the nature of the galaxy, the distribution of matter across interstellar space, and humanity's growing capability to explore and understand the cosmos. The first and perhaps most fundamental lesson is that interstellar objects are real, accessible, and amenable to detailed study. Before Oumuamua in 2017, the existence of such objects was theoretical. Astronomers knew that planetary systems must eject material, and logic dictated that this material would wander the galaxy. But seeing theory become observation, detecting and characterizing these ancient wanderers transforms abstract concepts into concrete reality. With 3 confirmed interstellar objects now in our catalogue, the reality of these visitors is established. The question is no longer whether they exist, but rather how common they are, what properties they exhibit, and what they tell us about the galaxy. Each new detection adds to this knowledge base, gradually revealing the characteristics of the population as a whole. 3 Atlas teaches us about the size distribution of interstellar objects. The fact that we detected such a massive object so early in our survey suggests either that large objects are more common than expected, or that detection biases favour finding big, bright targets. As survey capabilities improve and we begin detecting smaller, fainter objects, the true size distribution will become clearer. The composition of 3I Atlas, dominated by carbon dioxide rather than water ice, reveals chemical diversity among planetary systems. Not all star systems produce comets with the same composition. The temperature profile of the protoplanetary disk, the distance at which the comet forms, the parent star's luminosity and spectral type, all influence what molecules get incorporated into the growing body. This compositional diversity has profound implications for astrobiology. If we want to understand how common life might be in the galaxy, we need to know how common the building blocks of life are. Water is crucial, carbon compounds are necessary, nitrogen and phosphorus play essential roles. By studying the chemistry of objects from many different star systems, we map the distribution of these life-essential elements across the galaxy. 3E Atlas demonstrates that water, while present in this interstellar visitor, is not necessarily the dominant component. Other systems produce carbon dioxide-rich objects. This suggests that the availability of water for planet formation varies from system to system. Some stars may be surrounded by more water-rich material, favouring the formation of water worlds. Others, like the system that produced 3I Atlas, might have outer regions dominated by carbon oxides. The trajectory of 3I Atlas raises questions about what determines the paths of interstellar objects. Is the 5-degree alignment with our ecliptic plane pure chance? Or does it hint at some selection effect, some mechanism that preferentially guides objects into planetary planes? If gravitational focusing cannot fully explain the alignment, what other factors might be at play? One possibility involves the galactic environment. The solar system moves through the galaxy at over 200 kilometers per second, ploughing through the interstellar medium like a ship through water. This motion creates a bow shock and defines a preferred direction of approach for material in the galaxy's reference frame. Objects moving with the general galactic flow would naturally tend to approach from certain directions rather than others. The massive size of 3I Atlas teaches us about the limits of planetary ejection mechanisms. How do you eject a 5-kilometer object from a planetary system? The process requires enormous energy. Typically, close encounters with giant planets provide this energy, slinging smaller bodies into hyperbolic trajectories. But ejecting something as massive as 3I Atlas requires either an unusually close encounter or multiple successive encounters building up velocity over time. Alternatively, the object might have been ejected during a more dramatic event, such as a stellar encounter that disturbed the entire planetary system. If another star passed through or near the system, its gravitational influence could scatter large bodies into interstellar space. Such encounters are rare, but do occur over the billions of years that planetary systems exist. The age of 3I Atlas, potentially older than our Sun, places it in the context of galactic evolution. If formed 7 billion years ago, this object dates from a time when the galaxy had different structure, when the interstellar medium had lower metallicity, when the rate of star formation was higher. It is a time capsule carrying information not just about one planetary system, but about the galaxy as a whole during an earlier epoch. The detection of hydroxyl radicals by Meerkat demonstrates the value of multi-wavelength observations. Radio telescopes see aspects of comets invisible to optical instruments. Ultraviolet satellites like SWIFT detect emission lines blocked by Earth's atmosphere. Infrared observatories probe thermal emission and molecular vibrations. Each wavelength regime provides complementary information, and only by observing across the spectrum can we fully characterize these visitors. This lesson applies broadly to astronomy. As technology advances and new instruments come online, the most powerful approach involves combining observations from many facilities rather than relying on any single instrument. The synergy between different techniques reveals more than the sum of individual observations. The 7 jets of 3I Atlas illustrate the complexity hidden within what appears from a distance to be a simple fuzzy blob. Structure exists at all scales in comets. From afar we see a diffuse glow. With better resolution, jets appear. With even higher resolution, we would see surface features, boulders, fractures, regions with different albedo. Each level of detail reveals new physics, new processes at work. The rapid brightening at perihelion and the unusual blue colour challenge our understanding of cometary activity. Not all phenomena fit neatly into existing models. Sometimes observations exceed theoretical predictions, forcing refinement of the physics. The blue colour remains unexplained by standard dust-scattering models, suggesting either unusual particle properties or an emission mechanism not yet fully understood. This is how science progresses. Models make predictions. Observations test those predictions. When observations disagree with models, either the observations are wrong, instrument error, misinterpretation of data, or the models need updating. Usually it is the models that require adjustment as new phenomena are discovered. The connection to the wow signal, whether ultimately proved coincidental or significant, highlights how discoveries in one domain can cast new light on old mysteries. For 48 years, the wow signal stood as an isolated event, intriguing but ultimately inscrutable. The arrival of 3i Atlas from a nearly aligned direction adds context, suggesting possible explanations that were not previously considered. Even if the connection proves spurious, it demonstrates the value of reconsidering old data in light of new discoveries. Archives contain treasures waiting to be recognized. Phenomena that seemed inexplicable when first observed may become comprehensible with additional information from subsequent events. The public response to 3i Atlas reveals the enduring fascination with the possibility of life and intelligence beyond Earth. The speculation about whether the object might be technological, while not supported by current evidence, captures imagination in ways that purely natural phenomena sometimes do not. This reflects a deep human desire to know whether we are alone, whether other minds exist among the stars. Scientists working on 3i Atlas must navigate this landscape carefully. Dismissing public interest as uninformed or sensationalistic misses the opportunity to engage people with real science. But feeding speculation without evidence risks damaging credibility and misleading about what is actually known. The balance lies in honest communication, explaining both what we observe and what those observations mean within our current understanding. The letters that arrived in Avi Loeb's inbox from around the world, examples of which were shared in his articles, demonstrate that astronomical discoveries inspire people across cultures, ages and professions. A middle school teacher in Italy, a student in Mexico, a content creator in South Africa, a healthcare worker in Florida, all writing to express appreciation for science communication about 3i Atlas. This global interest represents both an opportunity and a responsibility. The opportunity is to use exciting discoveries to inspire the next generation of scientists to demonstrate that the universe is accessible to inquiry, that its mysteries can be unravelled through careful observation and logical reasoning. The responsibility is to do so truthfully, maintaining the integrity of the scientific process while making it comprehensible to non-specialists. The ongoing observation campaign for 3i Atlas, extending through December 2025 and into 2026, will add significantly to our knowledge. The closest Earth approach on December 19th offers the best observing geometry from our planet. The Jupiter encounter in March provides opportunities for spacecraft observations. Each phase contributes unique data to the overall picture. When the observations finally conclude, when 3i Atlas has faded beyond the reach of even the most powerful telescopes, the analysis will continue for years. Papers will be published comparing this object to solar system comets and to the two previous interstellar visitors. Statistical analyses will incorporate 3i Atlas into population models. Theoretical work will explore implications for planet formation, galactic dynamics, and the potential for panspermia, the transfer of life-bearing material between star systems. The ultimate lesson of 3i Atlas is that the universe continues to surprise us. Despite decades of studying comets, despite sophisticated models of planetary system formation, despite comprehensive surveys of the solar system, this visitor exhibited properties we did not fully anticipate. The unusual mass, the carbon dioxide dominance, the trajectory alignment, the rapid perihelion brightening, all challenged expectations. This capacity for surprise is not a failure of science, but its greatest strength. If observations always matched predictions perfectly, we would have nothing new to learn. Discovery happens at the boundaries of knowledge, where observations reveal phenomena not captured by existing theories. Each surprise is an invitation to deepen understanding, to refine models, to expand the scope of what we know. As humanity develops more powerful survey telescopes and more sensitive instruments, the rate of interstellar object discoveries will accelerate. What seemed impossibly rare a decade ago, with only 1 or 2 detections per decade, may become routine, with multiple discoveries per year. This growing catalogue will enable statistical studies currently impossible with such small sample sizes. We will learn whether 3i Atlas is typical or unusual among interstellar visitors. We will map the distribution of compositions, sizes and trajectories. We will constrain ejection mechanisms and survival timescales. Eventually, we may even identify specific parent systems for some visitors by tracing trajectories backward with sufficient precision. Looking further ahead, technologies under development may enable more than passive observation. Proposals exist for rapid response missions that could intercept and study interstellar objects up close, even collecting samples and returning them to Earth for laboratory analysis. Such missions face enormous technical challenges, requiring propulsion systems capable of matching the high velocities of these visitors and doing so on short notice when opportunities arise. If we could sample material from 3I Atlas directly, analysing its composition with laboratory precision, rather than through spectroscopy from millions of kilometres away, the scientific return would be extraordinary. Isotopic ratios, trace element abundances, organic molecules, all could be measured with far greater accuracy than remote sensing allows. The infrastructure being built for asteroid mining and space resource utilisation could eventually be adapted for intercepting interstellar objects. If we develop capabilities for reaching and manipulating asteroids for economic purposes, those same capabilities might enable scientific missions to visitors from other star systems. 3I Atlas represents a chapter in the ongoing story of human exploration and understanding. Our species looks outward, asking questions about our place in the cosmos, seeking to understand the nature of the universe that birthed us. Each discovery, from planets around other stars to gravitational waves from colliding black holes to interstellar visitors passing through our solar system, adds to that understanding. The object that entered our awareness on July 1st, 2025, that displayed 7 jets on November 8th, that released hydroxyl molecules detected by radio, telescopes that carries within its frozen heart material from another star system, has enriched our understanding immeasurably. Whether it proves to be entirely natural or contains elements of the unexpected, whether its connection to the WOW signal is real or coincidental, whether future observations reveal more secrets or confirm current interpretations, 3 Atlas has already secured its place in astronomical history. As it departs our solar system, heading back into the vast dark between stars, 3's Atlas carries with it not just ancient ice and primordial chemistry, but also the hopes and questions of a species beginning to understand its cosmic context. We watched it arrive, we studied it intensely during its brief visit, and now we watch it leave, enriched by the knowledge gained and inspired by the mysteries that remain. The universe is vast beyond human comprehension, filled with wonders we're only beginning to glimpse. Through Atlas, this wanderer from the depths of space and time, reminds us that our solar system is not isolated, but connected to the broader galaxy, that material and perhaps information flows between stars, that we live in a dynamic cosmos where discoveries await around every corner. As we continue to observe the sky, as our instruments grow more powerful and our surveys more comprehensive, we will encounter more visitors like 3I Atlas. Each will teach us something new about the galaxy we inhabit. Each will challenge our understanding and expand our knowledge. And each will remind us that the universe is not a static museum, but a living, evolving system of which we are a part. This is what 3I Atlas teaches us, that the cosmos is accessible to inquiry, that mysteries remain to be solved, that every question answered reveals new questions to ask, and that the human quest to understand our place among the stars continues, one observation at a time, one discovery at a time, one interstellar visitor at a time.